What if nothing around you is real, your memories, your thoughts, even who you are? What if the moment you feel has already vanished, and your brain isn't watching reality, it's creating it? For the next hours, we'll tear through the layers of the mind, where quantum physics, neuroscience, and psychology collide. This isn't fantasy. These are real cracks in reality, anomalies that rewrite everything you think you know about time, perception, and choice. So, let go of certainty. Step into the unknown, and follow us, where reality itself begins to break. Quantum reality, how your awareness shapes the universe. What if I told you that the universe you wake up to every morning is not as fixed or independent as you were taught, but instead is fluid, participatory, and unfinished until you engage with it? For most of human history, we believed that reality was like a great clockwork machine, ticking away with cold precision whether or not anyone was watching. We assumed that rocks, trees, stars, and even the smallest grains of matter existed in definite, stable states at all times, their properties independent of our gaze. Yet modern physics tells a very different story, one so strange that it challenges not just the limits of science, but the very boundaries of philosophy and meaning. At the heart of this story lies quantum mechanics, a framework that describes the invisible world of atoms and subatomic particles. And the deeper we look into this hidden layer of existence, the more we realize that what we call reality may not simply exist on its own, it may, in a very real sense, wait for us. Consider this. A particle, one of the building blocks of the cosmos, does not have a single location until it is measured. Instead, it drifts in a haze of possibilities, occupying many potential states at once, like a story with countless alternate endings. The moment you observe it, that haze collapses into one outcome, while all the other possibilities disappear. This isn't metaphor or poetry, it's what experiments reveal again and again. Take the legendary double-slit experiment. Fire electrons or photons at a barrier with two openings and you'd expect them to act like tiny bullets, hitting the screen behind in two neat clusters. But that isn't what happens. Instead, they spread out in a wave-like interference pattern, as though each particle somehow traveled through both slits simultaneously, interfering with itself. And yet, when we set up detectors to check which slit each particle passes through, the interference pattern vanishes, and the particles behave like ordinary marbles again. It's as if the act of looking forces the universe to decide. This bizarre behavior forces us to question everything we think we know about existence. If particles only take on definite states when observed, then what does that say about the nature of the world when no one is watching? For centuries, we assumed reality was objective, indifferent, solid. Quantum physics whispers otherwise. It suggests that possibility, not actuality, forms the bedrock of nature, and that observation is what collapses possibility into presence. The implications ripple far beyond physics. They seep into our understanding of choice, time, and even selfhood. Think about the decisions you've made in your life, the careers you didn't pursue, the relationships you never began, the roads you never walked. In classical thinking, those are just hypothetical branches of a story you never lived. But in the quantum view, perhaps those unchosen lives are not entirely gone. Perhaps they linger as echoes, ghostly potentials that remind us reality is not a single straight line, but a shimmering field of options waiting for collapse. And here's where the mystery deepens. Your awareness, your act of noticing, might not just reveal the world, but actively help construct it. When you pay attention, the universe narrows down from countless possibilities into one lived moment. That's not just physics, it's philosophy reshaped by experiment. Suddenly, free will feels heavier, because every decision collapses not only your path, but an entire landscape of what could have been. Perhaps the anxiety we feel when making choices is not merely psychological, it may reflect the very structure of reality itself. Choosing means watching infinite possible selves dissolve into one. And yet, within that grief, there is creation. To decide is to shape the universe. Time, too, begins to warp under this lens. In the everyday world, time feels linear, past, present, future flowing in order like beads on a string. But quantum mechanics allows for phenomena that suggest time may not be so rigid. In some interpretations, Events in the future appear to influence outcomes in the past. Experiments hint at retrocausality, where cause and effect twist into loops and paradoxes. If that's true, then your future is not merely awaiting you, it may already be tugging on the threads of your present, subtly guiding what you call now. What does this mean for identity? If the quantum world is a superposition of possibilities, then perhaps the self is, too. Maybe you are not a fixed, static being, but a shifting cloud of probabilities, crystallizing into a specific version of yourself moment by moment as you make choices, as you observe, as you collapse the wave. This is more than science, it is an invitation to rethink what it means to be alive. You are not a detached observer floating above reality. You are embedded in it, entangled with it, part of the very mechanism that gives rise to the world you experience. Skeptics argue that quantum mechanics is just math, that it describes small scales without necessarily reshaping the macroscopic human world. Yet even if that's true, the metaphors are unavoidable. When the foundational building blocks of matter refuse to behave like solid things, when they flicker between potential states until observed, the old story of a stable, mechanical universe loses its grip. The quantum narrative replaces it with something more intimate, a cosmos in which the observer matters. And if consciousness, awareness, or simply observation plays such a central role in shaping outcomes, then the line between physics and metaphysics blurs. This doesn't mean that reality is whatever you want it to be, nor that thought alone can bend the cosmos. But it does suggest that your presence, your attention, has genuine significance. The universe, at its core, is participatory. You don't simply live in it, you help bring it forth. Perhaps this is why so many thinkers, from philosophers to mystics, find resonance in quantum mechanics. It seems to echo ancient intuitions about the inseparability of self and world, while grounding those intuitions in the most precise experiments modern science can offer. So where does this leave us? If reality is not fully decided until it is observed, then life is not just a story you walk through, but a story you co-write. Each moment you choose, each step you take, each act of attention collapses countless possibilities into one lived world. To live is to participate in the ongoing creation of reality. To exist is to weave potential into presence. And that changes everything. It means your choices matter far more than you think. They are not trivial, they are acts of creation. It means uncertainty is not a flaw of the universe, but its essence, its creative engine. It means that the fear of the unknown can be transformed into reverence, because uncertainty is where all new realities are born. So maybe the lesson of quantum mechanics is not to cling to certainty, but to embrace the mystery. To accept that reality is not given, but made, moment by moment, through the dance between possibility and observation. You are not a spectator. You are a co-creator. A particle can be in two places at once until you look, and you too can hover between countless possible lives until you choose. The act of choosing is the act of becoming. The act of observing is the act of creating. And in that, there is both weight and wonder. Perhaps awareness itself is not just something happening inside the universe. Perhaps awareness is what the universe does when it becomes you. The delayed choice experiment. How the future rewrites the past. Imagine if the book of your life did not begin with chapter 1, but instead with the ending already chosen, and every earlier page rearranged itself to fit that outcome. That is the unsettling implication of a quantum puzzle called the delayed choice experiment, an experiment that questions the very fabric of time. In our everyday experience, time is supposed to be a conveyor belt, past behind us, future ahead, present slipping away with each tick of the clock. We think of the past as fixed, a foundation we build upon, something untouchable. But quantum physics has a way of tearing apart what feels obvious. In this strange realm, the future can reach backward and seemingly edit what has already happened. It is not metaphor or science fiction. It is an experiment, repeated and verified, where light itself seems to wait for you to decide how it behaved. The essence of the delayed choice setup begins with photons, the tiniest quanta of light, and a variation on the famous double-slit experiment. Normally, when light passes through two slits, if you measure which slit it travels through, it behaves like a particle, producing two clusters. But if you don't measure and just let it travel, it behaves like a wave, interfering with itself to form a beautiful striped pattern. The shocking twist in the delayed choice version is that the decision to measure or not is made after the photon has already gone through the slits. And yet, it responds as if it always knew your choice. If you later decide to measure its path, the photon behaves like it had gone through one slit only. If you decide not to measure, it behaves like a wave that went through both. In other words, the photon's past behavior is determined not at the moment it traveled, but at the moment you observe it. This is not speculation. It is hard experimental data. What does that mean? It implies that the universe may not have a definite history until it is required to. The past might not be locked until the present collapses it into a story. If that's true, causality is not a one-way street from A to B, but a feedback loop where the future informs the past. Think about that. We often reinterpret our lives the same way. A painful event that once seemed meaningless later becomes a defining moment of growth. A casual meeting years ago becomes significant only because of what unfolded afterward. Psychologists call this reframing, but maybe it is more than mental gymnastics. Maybe it echoes the same logic the photon obeys. That meaning, and perhaps even events themselves, do not finalize until the future demands coherence. If so, your memories are not dusty archives, but living processes, reshaped every time you revisit them. This idea challenges our sense of responsibility and identity. If the past is fluid, are you truly the product of fixed events, or are you continuously sculpting the past as you choose in the present? We like to think our story is linear, but the delayed choice experiment suggests we are constantly in negotiation with time itself. You are not just moving forward on a road already paved. You are paving the road behind you as you walk. Consider the philosophical weight of this. If time does not pre-exist as an arrow but is generated through choices and observations, then reality is less like a script and more like improvisation. You are not a passive audience member but an active participant who co-writes the play with the universe. Every decision reverberates both forward and backward, coloring your past and shaping your future simultaneously. Some researchers even speculate this could explain the strange sensation of déjà vu, prophetic dreams, or impossible intuitions, echoes not from the past, but from outcomes that have yet to occur, folding back to influence your perception now. Imagine catching a glass before it falls and realizing your hand was already moving before you consciously decided. That is the kind of paradox the delayed choice experiment whispers to us. This doesn't mean you control time like a deity. Instead, it places you inside the machinery of time itself, part of the gears rather than outside the clock. Observation doesn't give you absolute power, but it does mean reality waits for interaction before settling. The photon doesn't commit until you look. Similarly, perhaps your life doesn't commit to a single narrative until you engage with it consciously. And here lies the hopeful implication. Maybe your regrets are not carved in stone. The mistakes, the traumas, the missteps, they may remain open to reinterpretation, not just psychologically but in some fundamental sense. Healing might not be erasing the past, but observing it differently, collapsing it into a new meaning. Perhaps destiny is less about a predetermined line and more like a canvas painted from both ends, where present choices radiate backward as much as they project forward. In that sense, free will is not just about creating the future. It is about co-authoring the past. Every act of awareness is a ripple that reshapes what has already happened. This sounds almost mystical, but the delayed choice experiment anchors it in data. The photon behaves retroactively, aligning its history with the observer's present decision. If matter at the smallest level is capable of such flexibility, why not consciousness? Why not the stories we live by? Time, then, is not a strict corridor but a field of possibilities, a shimmering network where outcomes align to form coherence only when required. Perhaps this explains why our lives feel less like fixed lines and more like evolving narratives. The present is not just a thin slice between past and future, but the crucible where both are forged. And if the universe itself leaves space for retrocausality, then your past is not finished. It is waiting for you to choose how to measure it, to decide what story it tells. That is the profound challenge and gift of the delayed choice experiment, to realize that reality may not be settled until you are part of it. The photon doesn't care until you ask. Likewise, your story is still pliable, even in its earliest chapters, shaped by the choices you make now. In the end, the question is not whether time is an arrow or a loop, but whether you are willing to step into the role of co-creator. The experiment demonstrates that the universe does not answer questions until they are asked. And maybe the same is true of you. The future is not just ahead of you, it is behind you, too, rewriting, reframing, recalibrating. The now is where both directions converge, and observation is the bridge. If that's the case, then the story of your life is still unfolding, even in the parts you thought were already written. The observer effect, how your awareness shapes reality. Imagine walking into a hall of mirrors where nothing reflects you back until you move. The glass stays blank until your hand rises, your head tilts, and suddenly the reflections scramble into existence. That strange delay is not just a metaphor. It is a glimpse into one of the most profound discoveries in science, the realization that observation itself changes reality. In the world of quantum mechanics, this is known as the observer effect, and it is not poetry or philosophy but experimental fact. At the smallest scales of existence, particles do not behave like solid marbles rolling around. They exist as clouds of probability, a haze of potential states waiting to be pinned down. Only when an observation is made, when a detector is switched on, when awareness intervenes, does the particle resolve itself into one definite outcome. Before that, it hovers in limbo, both many things and nothing in particular. The classic example of this is the double-slit experiment. Fire photons or electrons at a barrier with two slits, and if you don't observe their path, they create an interference pattern on the screen beyond, as though each particle traveled through both slits simultaneously like a wave. But if you set up a detector to determine which slit the particle traveled through, the interference disappears. The pattern changes completely, as if the act of observation forced the particle to pick one slit and abandon its ghost-like wave duality. This is not an isolated trick. It has been replicated countless times and remains one of the most unsettling results in physics. The mere presence of observation alters what is real. Now, the unsettling part is what this means outside the lab. If particles themselves are shaped by being watched, then perhaps this principle scales up into the human domain. Think of the last time you felt eyes on you in a crowded room. Your body stiffened, your awareness sharpened, your behavior shifted. The observation did not simply record who you were. It sculpted who you became in that instant. Just as a particle collapses into a definite state, so too do we collapse into versions of ourselves under attention. Observation calls forth the observed. This is not just psychological. Neuroscience shows that even memory behaves this way. When you recall a moment from your past, you do not retrieve a static file. You reconstruct it. Each act of remembering is an act of rewriting, reshaping the memory through the lens of who you are now. Traumas can soften into lessons. Meaningless events can take on new significance. What you remember is never the original moment, but the story your present awareness chooses to weave around it. In this way, the observer effect is not confined to electrons. It is stitched into the fabric of human identity. Our lives are not merely observed, but co-authored by the act of observation. This insight complicates our ethics. If our perception is never neutral, if every glance, every thought, every interpretation changes reality, then we are responsible for the worlds we conjure. Look at someone with suspicion, and you collapse them into defensiveness. Look with compassion, and you invite them into kindness. Surveillance imprisons people in caricatures. Love frees them into possibilities. Attention is not harmless. It is participatory. It is a sculptor's hand shaping clay. And if physics teaches us anything, it is that the observer is always part of the system. There is no outside vantage point. The measuring device is not separate from the experiment. You are not a detached spectator in life. You are a participant whose gaze is woven into the outcome. Reality does not sit around waiting to be discovered. It crystallizes under the weight of attention. This reframes truth itself. We often imagine truth as something hidden, waiting to be unearthed, like a fossil beneath the sand. But maybe truth is more like ice forming on a window pane, appearing only when the right conditions of observation make it visible. Knowledge is not a picture we take of the world. It is a relationship, a co-creation between consciousness and matter. That does not mean facts are illusions, but it does mean that reality is not indifferent to perception. Even the hardest edges of the universe carry the imprint of awareness. What does this mean for your life? It means your past is not fixed. Your memories shift each time you revisit them. It means your identity is not predetermined. You collapse into versions of yourself based on the quality of attention you receive. It means your relationships are living feedback loops where being seen is itself transformative. And most radically, it means your awareness is not passive. It is an instrument of creation. Every time you look at the world, you participate in writing it into being. Every choice of focus changes what becomes real. This is terrifying, because it strips away the illusion of objectivity, the comfort of detachment. But it is also liberating, because it hands you agency. If observation is power, then you are never powerless. You shape reality simply by engaging with it. You shape people simply by how you see them. You shape your own life by how you interpret it. The observer effect is a call to responsibility, but also an invitation to possibility. You are not just watching the movie of reality play out. You are holding the projector. Each glance, each thought, each act of awareness directs the light that forms the scene. So live with that knowledge. Watch more carefully, listen more deeply, look with love, because love collapses reality into its most generous form. If particles wait for observation to decide what they are, maybe the universe itself is waiting for you to decide what story it wants to tell. Maybe reality is not the stage set before you arrive, but the script that writes itself every time you open your eyes. And in that sense, the most radical act of creation you will ever commit is to observe, because to observe is to bring forth the world. Quantum entanglement, the hidden web that connects everything. Quantum entanglement has long been described as one of the strangest features of the universe. Imagine two fragments of a mirror shattered long ago. Even though the pieces have been carried far apart, they somehow still act as if they are whole. When one fragment catches the light at a certain angle, the other responds as though space and distance are irrelevant. That metaphor only scratches the surface of what entanglement represents. At its core, quantum entanglement is the discovery that when two particles share a history, they never really part ways. Their states are correlated in a way that can't be explained by signals traveling between them. It happens instantly, faster than light, almost as if space itself were only an illusion. The physics is rigorous, confirmed through countless experiments, yet the implications extend far beyond the lab. They bleed into philosophy, psychology, and even how we understand human connection. The classical worldview tells us that the universe is made of objects, each with its own separate existence, bumping into each other like billiard balls. Quantum entanglement smashes that worldview. Instead, reality seems built not of things, but of relationships. When particles interact, they don't just exchange information and move on, they form a shared identity. Measuring one immediately tells you about the other, no matter how far apart they drift. Einstein disliked this idea so much he called it spooky action at a distance, suspecting that hidden variables would someday explain it away. But decades of experiments, from Bell's theorem to Alan Aspect's Nobel-winning work, proved otherwise. There are no hidden gears behind the curtain. The correlations are real, undeniable, and not bound by the speed of light. What does this mean for us? At first, it seems like abstract physics with no bearing on daily life. But sit with it longer, and it starts to erode the boundaries we take for granted. If fundamental particles are linked beyond space and time, what does that say about us? After all, every atom in our body has a quantum past, a lineage stretching back to the birth of the universe. If entanglement never fades, could we be part of an invisible web that connects all living beings? Consider moments of eerie coincidence. You think of a friend you haven't spoken to in years, and they suddenly call. Or you walk into a room and feel a wave of tension before anyone speaks. Science often chalks this up to pattern recognition and probability, but some thinkers suggest entanglement might be a deeper layer at play. Perhaps our consciousness isn't locked inside our skulls, but participates in a shared field, radiating correlations just as entangled particles do. This idea blurs the line between physics and philosophy, but that's exactly what entanglement forces us to do: question where one ends and another begins. Some physicists even argue that space-time itself is not fundamental, but arises out of entanglement. According to this radical view, space is not a stage on which events unfold but an emergent geometry woven from countless threads of quantum connection. If that's true, then distance is only a matter of perspective. Two particles, or even two people, might be close in terms of entanglement, even if they are galaxies apart. It flips our everyday intuitions inside out. Separation may be a useful illusion, but not the ultimate truth. This has enormous consequences for how we see human relationships. Love, empathy, grief, these may not just be emotions trapped in our private worlds. They could be signals of something real, evidence that our inner lives are interwoven at a fundamental level. When you cry during a film or flinch at a stranger's pain, perhaps it's not just mirror neurons at work. Perhaps it's because your being is stitched into a fabric larger than yourself. Entanglement whispers that your life is not a closed system, but a node in a vast lattice where every action reverberates outward. And that raises uncomfortable responsibilities. If your state of mind can ripple through this invisible network, then the energy you carry, anger, compassion, indifference, may shape the world more than you realize. The observer effect showed us that watching changes the outcome of an experiment. Entanglement goes further. It says that simply being, in connection with others, already alters reality. You are always participating in a collective wave function. Every word, every choice, every act of attention collapses possibilities not just for you, but for the network you're entangled with. This is not an easy idea to absorb. Our culture prizes independence, individuality, and selfhood. We build walls to defend the idea that I am separate from you. Entanglement undermines that narrative. It suggests your fate is not your own. You are not an isolated point, but part of a configuration. To harm another is to wound yourself in ways you cannot measure. To love another is to reinforce coherence in the whole. Reality is not carved into pieces. It vibrates as patterns. The more deeply you look at entanglement, the less random life appears. Coincidence starts to feel like correlation. Synchronicity begins to look less mystical and more like a glimpse into a deeper order. Could it be that the Big Bang didn't scatter billions of particles but instead birthed a single universal wave function, still humming as one, entangled across all of space and time? If so, then you are not a speck in the cosmos, you are the cosmos looking at itself through your perspective. Your joys and sorrows are not trivial personal events. They are movements in a symphony playing across the stars. This doesn't mean everything is predestined or that free will is an illusion. Instead, it reframes free will as co-creation. Your choices are never made in isolation. They are duets, chords, echoes. When you act, you are entangling with the world around you, weaving a future together with others whether you recognize it or not. To see life this way is to stop asking, what's mine and what's theirs? And instead ask, what are we creating together? Entanglement challenges not only science, but spirituality. Many traditions have long taught that all beings are connected, that separation is a trick of the senses. Quantum mechanics, in its own cold mathematical language, seems to echo that wisdom. It tells us the universe is not made of things but of connections. That wholeness is the default, and separateness is the illusion. For centuries, mystics have said, we are one. Now, physics offers its own strange agreement. So how should we live in light of this? By becoming aware that every inner state carries weight. When you nurture kindness, you don't just improve your private world, you strengthen coherence in the larger web. When you stew in bitterness, you don't just poison your own heart, you send discord into the lattice that binds us all. This isn't a metaphorical claim. If entanglement is the foundation of reality, then every vibration matters. The lesson of entanglement is humbling yet liberating. You are not alone and never were. Loneliness is not the truth but a lens that hides the connections humming beneath. You were never meant to stand apart, because standing apart is impossible. Even in silence, you are entangled. Even in grief, you are woven into a whole. To see this, truly see it, is to feel the boundaries soften. You stop perceiving a world of objects and start perceiving a universe of patterns. You stop clinging to control and begin seeking harmony. You start listening not for walls, but for resonances. Maybe, just maybe, the universe has been whispering this truth all along. In the empathy that makes you cry with strangers, in the intuition that links you across miles, in the mysterious timing of synchronicities. Physics tells us these may not be accidents but reflections of the entangled whole. And if that's the case, then the question is not whether you are connected, but how you choose to participate in the music. Quantum entanglement is more than a scientific oddity. It is a revolution in worldview. It tells us the universe is not a machine of separate gears but a living fabric of correlation. It tells us that being alone is impossible. And it leaves us with one profound, unavoidable responsibility: to tend to our state of being as if it matters because it does. In this entangled universe, every thought is a ripple, every action a chord, and every breath an echo in a cosmic song without end. Every path at once. How quantum choices shape reality. Imagine standing at an immense crossroads at night, the moon hanging high, and 1,000 roads stretching in every direction. Some roads lead through misty mountains, others through crowded neon-lit cities, and some vanish upward into star-studded skies. You haven't chosen yet, but in some sense, you've already traveled all of them. This is the essence of the quantum world, a place where particles do not behave like tiny billiard balls marching from point A to point B, but instead explore every possible path, as if existence itself is rehearsing all outcomes before revealing just one. This isn't mystical poetry, it's grounded in mathematics and experiment. Richard Feynman, one of the great minds of modern physics, formalized this strange truth in what's called the path integral formulation. In his view, a quantum particle such as an electron doesn't just select a neat, singular trajectory. Instead, it behaves as though it samples every imaginable journey, even wild ones that loop around stars or tunnel through mountains. Each path contributes to the probability of where the particle is ultimately found. To us, this feels impossible. In classical physics, if you toss a baseball, gravity and motion dictate a clear arc. But on the quantum scale, if you threw a quantum baseball, it would simultaneously roll under your feet, soar past the moon, and sink through the earth. The catch is, when measurement happens, only one result survives. The rest collapse, like a grand orchestra of probability forced to play a single note. This collapse is at the heart of the quantum puzzle, and the role of observation makes it even stranger. Does the universe really wait for our gaze before it chooses? Some interpretations argue no, it's just interaction with a measuring device. Others suggest consciousness itself participates, carving out one reality from the infinite cloud of possibility. Here lies the overlap between physics and philosophy. Awareness might not just witness reality, but actively sculpt it. Think of your own life decisions. The jobs you almost took, the people you nearly met, the words you nearly said. To you, those paths seem lost. Yet in quantum mechanics, unchosen possibilities still matter. They interfere, they shape probabilities, they leave fingerprints even if they never become visible outcomes. This echoes in our own psychology. What we didn't do often shapes us as much as what we did. Regret, memory, and imagination are shadows of unrealized timelines that still haunt our choices. And in physics, those ghost paths literally exist in the math. They never vanish entirely until forced to. The double-slit experiment drives this home. When electrons pass through two slits without being observed, they create interference patterns, as though they travel both paths at once and interfere with themselves. The instant we check which slit they go through, the interference vanishes, and they behave like ordinary particles choosing a single route. The act of observing changes reality's script. The strange part is, this isn't confined to labs. Quantum mechanics describes the fundamental building blocks of everything, including you. So every solid chair, every hand you wave, every star above is underpinned by a reality that is far less certain than it appears. Our comfort with fixed outcomes may just be a survival tactic, a way of ignoring the storm of probabilities that underlies existence. Some physicists extend this further with the many worlds interpretation. Instead of collapsing possibilities, it proposes that every potential outcome actually happens just in different universes branching endlessly alongside ours. That means when you choose one career, another, you, chooses differently. When you stay, another version leaves. In this framework, you never truly lose the roads not taken, they're simply being walked by other versions of you. Whether or not this is true, the concept reframes decisions. Each choice is less an erasure and more a creation, the birth of parallel realities. Even if we never see them, they offer perspective on how weighty or how light our choices might be. What fascinates me most is how deeply this challenges our sense of inevitability. We like to imagine life as a straight road. What happened had to happen, what didn't was impossible. But quantum mechanics whispers otherwise. Possibility is real, not abstract. Until pinned down, the world hovers in a shimmering state of maybe. This makes observation the act of narrowing more profound. Every time we decide, every time we look closely, we collapse options. This collapse isn't destruction in the violent sense, it's more like editing. Out of countless drafts, one version is selected. In a way, awareness is the ultimate editor, pruning infinity into a digestible storyline. But editing comes with cost. What is erased when you pay attention? What futures never arrive because you fixed your gaze too soon? This perspective can shift how we live. Maybe hesitation isn't always weakness. Before you decide, the world is open, malleable. Once you choose, you shut doors. That is power, but it's also responsibility. The quantum world reminds us that potential has value, even when unseen. We live in a culture obsessed with certainty, but uncertainty is fertile, it's where all futures are born. Physics shows us that non-events matter. Paths untraveled shape interference patterns. In music, silences shape the melody. In life, what you almost did reshapes what you actually do. The ghosts of possibility linger, whether in equations or in memory. Perhaps that's not a bug in reality, but its deepest feature. And then comes the ultimate question. What is observation really? Is it enough for a machine to measure a particle, or does consciousness uniquely collapse the wave of probability? Some argue the former, that measurement is just physical interaction. Others suggest that mind and matter are intertwined, and that your awareness is woven into the universe's very fabric. If so, then each act of perception is not passive, it's creative, a collaboration with reality itself. The implications are staggering. It means that existence isn't simply revealed to you. It is partially authored by you. And whether or not consciousness is required, one thing remains. Narrowing possibilities changes what unfolds. Awareness is not neutral, it sculpts the world. The quantum particle offers a lesson hidden in its shimmering multiplicity. The world is not rigid, not fixed, not singular. It is a canvas of possibility, and your gaze is the brushstroke that defines the final picture. So the next time you face a decision, remember this. Before you choose, you are everything. The dreamer and the dream, the walker and the watcher. When you finally take a step, you collapse the infinite into one reality. But that doesn't mean the other roads didn't matter. They still whisper beneath the surface, shaping what is. Perhaps reality itself requires both the seen and unseen, the chosen and the unchosen to exist at all. In that way, your life mirrors the quantum world. One thread illuminated, woven from a tapestry of infinite might-have-beens. And maybe, just maybe, every act of attention is not just seeing, but creating. Superposition, the quantum truth about reality, choice, and who you could be. Imagine standing in front of a violin suspended in silence. It doesn't play a single note, yet within it lies every melody that could ever be played. This is more than poetic, it mirrors one of the strangest rules of our universe, superposition. In quantum mechanics, particles don't pick a side. They don't exist here or there, in one state or another. They exist in all possible states at once, a ghostly overlap of every potential outcome, until someone dares to look. Only then does the system collapse into one reality. This is the paradox of superposition. A thing can be perfectly quiet and infinitely loud, perfectly alive and already dead, perfectly decided and yet uncommitted. At first glance, this seems absurd. But it isn't metaphor, it is physics. Electrons don't just travel along one path, they explore all paths simultaneously. Photons can be in multiple places at once. Even molecules, collections of thousands of atoms, have been observed existing in overlapping states. What we call reality is not a straight line but a field of probability. And when observation collapses it into one outcome, the other possibilities don't fail, they simply never get chosen. To exist in one form means sacrificing all others. That is the haunting rule at the heart of the quantum world. This doesn't match our everyday intuition. In daily life, your chair doesn't both exist and not exist in your living room. Your coffee doesn't taste both bitter and sweet at the same time. But this is only because the macroscopic world we inhabit has already collapsed. Objects larger than particles interact constantly with their environment, destroying superpositions in a process physicists call decoherence. The strange possibilities never reach us because they vanish the moment they brush against the ordinary. And yet, the anomaly is not the particles, it's us. The world we perceive is the strange exception, a collapsed version of something that could have been far more expansive. Schrödinger's cat, the thought experiment you've probably heard of, wasn't meant as a quirky puzzle for kids. It was a scream against how alien quantum physics is compared to everyday logic. A cat sealed in a box with a quantum trigger doesn't simply wait alive or dead. It exists in both states simultaneously until the box is opened. Not metaphorically, genuinely, according to the rules of physics. It is only our impatience for certainty that forces us to demand, pick a side. But what if the universe itself doesn't share that urgency? Superposition implies reality is a cloud, not a point. It is a distribution of possibilities, each humming with a probability of becoming real. This isn't just strange math. It forms the foundation of quantum computing, where qubits are not restricted to binary 0 or 1 but can be both. The overlap creates a kind of parallelism so vast it may rewrite what we think is computable. But the principle also offers something profoundly existential. It forces us to confront the possibility that clarity is not natural, but artificial. That what feels like singular identity is only the collapse of deeper, overlapping versions of ourselves. Think of moments when you were torn between two decisions. The version of you who speaks up and the one who stays silent. The version who leaves and the one who stays. To you, it feels like you must choose. Yet what if both versions are real, two overlapping states of your being, humming like unresolved chords in your psyche? Life forces us to collapse, to choose one path, but the others still ripple in the unseen. To live is to continually collapse one version of yourself while countless others fade, not as impossibilities but as unrealized potentials. Superposition is not just physics, it's a mirror for existence. You are not one self. You are a chorus of selves, each valid, each possible, each waiting to be observed. But in the physical world, superposition is fragile. A single interaction, a glance, a breath of interference destroys it. The delicate state shatters and resolves into one outcome. That violin string of infinite potential must eventually play a single note. Yet, in that brief suspended moment before collapse, it carries a paradoxical power. It is more than real. It is the whole universe of what could be. This suggests something radical. Silence isn't emptiness. It is all music unplayed. A blank canvas isn't absence, it is all paintings waiting to exist. A human life unlived is not nothing, but everything. Until the brush touches, until the note is struck, until the measurement is made, existence is an unresolved chord. Here lies a strange kind of humility. Our desire for certainty makes us cling to definitions, to singular truths. We want to say, this is real, that is not. But quantum mechanics whispers something different. Truth is a distribution, reality is probability, existence is possibility. And that whisper isn't limited to physics, it leaks into meaning, morality, and identity. Can we judge choices harshly, knowing each was born from a sea of competing probabilities? Can we see ourselves as fixed beings when quantum physics itself insists that multiplicity is the default? There is an unsettling compassion in superposition. It suggests you are not defined by your last collapse, by the single outcome that happened to crystallize. You are not trapped as only one thing. You are many. At every moment, you carry within you the ghost of better, braver, kinder versions of yourself. And though only one emerges, the others are no less real. They exist as shadows in the field of possibility, reminding us that identity is not a statue but a wave. To live is to continually collapse into one version of yourself, again and again, while countless others echo in silence. This is terrifying, yes. It means we are not fixed. It means nothing is certain. But it is also liberating. Because it means change is not only possible, it is fundamental. At every instant, reality carries not just what is but what could be. The most real thing about you is the trembling uncertainty of who you might become. So, the next time you stand at a crossroads, before collapsing into a choice, remember the violin string. Remember the cat in the box. Remember the particle that hums in all places until observed. Don't rush to collapse. Stay open. Stay indeterminate. Let the waves sing. Because you are not one path. You are the entire field of possibility. And perhaps the most powerful thing you can do is pause just long enough to recognize the music of all that you could become. The observer effect. How consciousness shapes reality. Imagine a mirror placed deep in the forest, one that doesn't simply reflect what's in front of it, but instead bends to the expectations of the one who looks. It doesn't shine back images made of light. It answers with the landscape that your focus demands. Peer into it and the sky shifts, the ground bends, and the trees rearrange themselves. This isn't fantasy, it's a poetic way of describing something that quantum mechanics suggests about the very fabric of existence. Reality doesn't sit there waiting to be observed, it crystallizes when attention arrives. At the smallest levels of matter, the building blocks of reality do not behave like billiard balls rolling across a table. They act as if they are clouds of probability, smeared possibilities hovering in mathematical space. When no one is looking, they are many things at once. When observed, they collapse into a single outcome. This principle, called the observer effect, isn't just some quirky footnote in physics. It has been tested repeatedly and challenges everything we thought we knew about how the universe works. Think of the double-slit experiment, one of the strangest demonstrations of this phenomenon. Fire electrons through two slits, and they form interference patterns, behaving like ripples spreading across water, overlapping and cancelling each other out. Yet, the instant a detector is placed to measure which slit each electron travels through, the interference disappears. The electrons snap into particle-like behavior, as if the universe has been forced to make a choice. What changes isn't just our knowledge, it's the outcome itself. Simply by observing, we alter reality. This sounds like mysticism, but it's not. It's physics tested in laboratories worldwide. Now, here's where things grow even more interesting. The observer effect doesn't stop at particles. It leaks into how we think about consciousness. When neuroscientists study memory, they find something eerily similar. Every time you recall a past experience, your brain reconstructs it rather than replaying it. With each observation, the memory shifts. Observation reshapes not just particles in physics, but also stories in our minds. The past itself becomes pliable, subject to the way we focus on it. This leads to a radical question. If observation doesn't merely uncover reality but actively defines it, what does that mean for us as conscious beings? Are we passive spectators in a pre-written play, or are we co-authors writing the script as it unfolds? The classical worldview says the universe ticks along like clockwork, indifferent to our awareness. But quantum mechanics whispers a different story, that attention and measurement cut through infinite possibilities and carve out a singular thread of reality. In this sense, awareness is not neutral, it is generative. The implications are staggering. Look at your daily life, how you perceive others, the questions you ask, the narratives you believe, all of these act like quantum measurements. Treat someone as intelligent and they often rise to meet that expectation. Treat them as incapable and they shrink. The gaze itself has power. The observer effect in physics may operate in the microscopic realm, but in psychology and society, it operates in plain view. Your perspective sculpts outcomes. The world reflects back not just what is there, but the frame through which you ask the question. Consider this. If you wake up and ask, "Why is everything broken?" you will see cracks everywhere. If you ask instead, what can I build today? Your focus reorganizes the possibilities around you. In physics, electrons align differently when measured. In life, opportunities align differently when perceived. Both suggest that attention is not passive, it is a creative force. But let's pause and address the tension. Does this mean human consciousness literally collapses wave functions? Some interpretations of quantum mechanics, like von Neumann's hypothesis, suggest so. Others argue it's simply any irreversible interaction that triggers collapse, not human thought itself. Yet, regardless of which view you hold, the mystery remains. Before interaction, particles are undefined. After, they are something specific. Reality doesn't just wait for discovery, it waits for interaction. This breaks the illusion of a universe as a finished book. Instead, it's a blank manuscript, where each act of observation writes a line of text. That idea may sound poetic, but it's also profoundly scientific. In the lab, wave functions collapse under measurement. In our lives, identities collapse into form under self-awareness. Consciousness becomes both stage and playwright, shaping the narrative as it unfolds. So what does this mean for you? It means you're not just a camera recording what is. You're a sculptor, carving outcomes with your perception. You're not just seeing the world, you're helping write it. And with that power comes responsibility. How you frame others can shape who they become. How you frame yourself can alter who you grow into. In a sense, each act of attention is a vote cast for one reality among infinite potential ones. The observer effect is physics, yes, but it's also philosophy and psychology disguised in equations. It suggests that nothing is fully fixed until it is noticed. That possibilities remain suspended until choice arrives. And that awareness, the act of paying attention, draws the line between shadow and substance. Imagine looking in that strange mirror again. It doesn't reflect your features but your focus. It doesn't show who you are. It shows who you are choosing to become. What quantum mechanics offers us is not just a strange theory about electrons, it is a profound reminder about life. The world beneath appearances is one of potential, probability, and uncertainty. Attention, curiosity, and focus summon form out of possibility. And if that doesn't shake your assumptions about what it means to be alive, then perhaps you haven't looked closely enough yet. Quantum shadows: how observation shapes reality. Imagine walking into a space where nothing is truly solid until you acknowledge it. A chair that is undefined until you intend to sit. A lamp that only comes into focus when your hand moves toward it. Walls that are not barriers but vague outlines until your presence makes them so. This is not science fiction, but a metaphor for one of quantum physics' most disquieting ideas. Particles do not come with predetermined properties. They exist in limbo until measurement forces them into a definite state. At the core of quantum theory lies a paradox that collides with our everyday assumptions. We tend to think reality is fixed, that the moon exists whether we glance at it or not, that objects possess qualities like mass, color, and speed regardless of human attention. Yet experiments show otherwise. At the smallest scales, particles behave as probabilities, not certainties. Before they are measured, they occupy a haze of possibilities, superimposed states where they're here and there, fast and slow, spinning up and down simultaneously. Observation does not reveal what was already there, it decides what becomes real. This is not abstract speculation. It has been repeatedly confirmed through experiments such as the double-slit test and Bell's inequalities, where particles entangled at great distances display instantaneous correlations. If these particles had fixed, local properties, the outcomes would be predictable. Instead, the results defy classical logic, showing that the act of measurement itself influences reality. The wave function, a mathematical description of all possible states, collapses not gradually but suddenly into one outcome when observed. In this sense, reality is participatory. It is not a static book already written, but a script unfolding in real time. But here's where the conversation deepens. What does this mean beyond physics? If reality is not fully determined until engaged with, then the role of the observer is far from passive. To look is to intervene. To measure is to choose. This has staggering implications. It suggests that consciousness, or at least interaction, is woven into the fabric of how existence manifests. We are not simply spectators but participants in shaping what is. In the quantum theater, every act of inquiry writes the next line of the play. Of course, skeptics argue that quantum effects wash out at large scales. A baseball, unlike an electron, has a definite trajectory because the uncertainties of its countless particles cancel each other out. Our macroscopic world feels solid and predictable because quantum fuzz averages into stability. Yet even if we are insulated from quantum strangeness in daily life, the fact remains, at the foundation of everything, determinacy only arises when forced. Reality at its base is not written in stone, but penciled in until someone flips open the notebook. This strangeness has a mirror in our human experience. How often do we assume our identities are fixed, that our beliefs, values, and choices exist fully formed within us? In truth, much of who we are emerges only under pressure, under reflection, under scrutiny. A person may not know the depth of their courage until challenged. Compassion, loyalty, even ambition may remain in superposition latent potentials until circumstances demand they collapse into action. Just as particles crystallize into one outcome when observed, so too do our personal truths come into definition when life asks the question. The lesson is not that reality is an illusion, but that it is more dynamic than our instincts suggest. The quantum world teaches humility. It warns us against assuming permanence where there may be possibility. It invites us to consider that certainty is not guaranteed but negotiated at the edge between potential and observation. When we engage with the world, we are not just detecting reality, we are co-authoring it. Each inquiry, each choice, each observation chisels away at the undefined, pulling one version of events into existence while discarding countless others. This participatory model reframes the role of knowledge itself. To ask a question is not neutral, it shapes what answers are possible. The universe seems less like a clockwork mechanism and more like an improvisational performance. Each act of engagement is a brushstroke, each measurement a decision that narrows the infinity of what could be into what is. Reality, then, is not separate from us. It is entwined with us. The observer is always inside the frame, never outside it. Perhaps the most provocative philosophical question raised here is whether observation itself creates reality. Does the moon exist in all its detail when no consciousness gazes upon it? Does an unmeasured particle drift as a ghost of possibilities, awaiting the summons of inquiry? Physicists debate these questions intensely, and interpretations vary from the Copenhagen stance, which accepts the collapse of the wave function at measurement, to many worlds theories that suggest all possible outcomes occur in branching universes. Regardless of interpretation, the unsettling fact remains: measurement is not passive. It is constitutive. Let us bring this idea back to the metaphorical room where nothing is defined until you step inside. Each movement, each glance, each question is not just discovering reality but crafting it. You extend your hand and the object materializes. You walk forward and the path assembles beneath your feet. The world is less a static landscape and more an evolving terrain sculpted by your awareness. Particles, incomplete without observation, mirror us in an unexpected way. We, too, may be unfinished until called upon by the gaze of others, by the challenges of life, by the demand of a decision. In the end, quantum physics offers both a scientific revelation and a philosophical mirror. Scientifically, it dismantles the notion of fixed, pre-existing properties, replacing them with probabilities awaiting collapse. Philosophically, it reminds us that reality is interactive, contingent, responsive. Observation is not a window through which we view the world. It is a brush that paints the canvas, a chisel that shapes the stone, a stage on which both the universe and we ourselves improvise the next act. To live with this understanding is to accept that certainty is rare, that possibility is abundant, and that every step forward is not merely walking into a pre-written script but participating in writing it. In this sense, reality is not a thing to be found. It is a process we are immersed in. The moon may still shine whether we see it or not, but at the smallest scale, the world waits for us to look before it decides what to be. And perhaps so do we. Quantum tunneling, when reality breaks its own rules. What if the barriers you thought were unbreakable weren't really barriers at all? Physics tells us that matter should behave predictably, that walls are solid, that resistance is final. Yet in the strange depths of quantum mechanics, this neat order dissolves. Particles, those elusive building blocks of reality, have been observed slipping through barriers without the required energy, passing into places they should never reach. This phenomenon is called quantum tunneling, and it is not only a fundamental principle of our universe, but also a challenge to the way we think about limits, effort, and possibility. To understand tunneling, we need to first step away from our everyday intuition. In the classical world, the one we see and touch, a ball rolls toward a hill and only gets over if it has enough momentum to reach the top, fall short, and gravity pulls it back. This seems obvious, but in the quantum realm, particles are not tiny balls following deterministic paths. They are better described as wave functions, mathematical clouds of probability that extend across space. These waves do not abruptly stop at obstacles, they merely fade. And so, even when a barrier stands tall, there exists a faint chance that the particle's wave leaks through. And if the wave exists on the far side, no matter how improbable, there is a possibility the particle itself will be found there. It doesn't climb, break, or smash. It tunnels. At first glance, this sounds almost magical, as though particles are cheating the laws of physics. But this is not magic, it is probability woven into the foundation of reality. Tunneling is not rare or exotic. It is happening constantly, all around us, and without it, life itself would not exist. The sun, for example, relies on tunneling to shine. Inside its blazing core, hydrogen nuclei need to overcome powerful repulsive forces in order to fuse. Classically, they don't have enough energy to do this. If physics stopped at Newton's rules, the stars would remain cold and dark. But tunneling allows those nuclei to slip through their barriers and merge, releasing the energy that lights our world. On a much smaller scale, tunneling is also responsible for the operation of semiconductors and transistors, the very heart of modern electronics. Every smartphone, every computer, every digital tool you touch depends on this improbable process. But beyond the technical marvels, tunneling forces us to confront a deeper philosophical truth. The rules we think are rigid often bend under closer scrutiny. In daily life, we approach challenges as though effort must directly equal result. Push hard enough, you succeed. Fall short, you fail. Yet tunneling whispers something different, that sometimes persistence, patience, and the possibility of chance can achieve outcomes brute force cannot. This shift in perspective matters. Consider how often people encounter walls in their lives. Professional setbacks, emotional wounds, financial struggles, or creative blocks. These barriers feel immovable, convincing us that progress is impossible without overwhelming energy. But quantum mechanics tells us that presence itself can alter probability, that being in the game, continuing to lean forward even when it feels hopeless, allows tiny chances to accumulate. And sometimes, those slim chances are enough. To tunnel through life's obstacles is not to deny their existence, but to recognize that no wall owns all outcomes. We assume resistance is the end of the story, when it might only be a chapter. The truth is that barriers are rarely absolute. They are often thresholds of probability, waiting for a subtle shift in context, timing, or persistence to open a narrow corridor. This is not naive optimism. It is alignment with the deeper logic of the universe. Quantum tunneling does not guarantee success, but it guarantees possibility. That alone should reshape how we think about failure. Too often, we quit at the edge, mistaking improbability for impossibility. But the wave function teaches us that even faint echoes of chance are enough to keep moving forward. There is another way tunneling challenges us. It questions separateness itself. When a particle disappears on one side of a barrier and appears on the other without traveling in between, what does that mean for continuity? For presence? For our sense of cause and effect? It suggests that reality is not strictly sequential, but relational, a mesh of probabilities where outcomes are entangled rather than isolated. In this view, barriers are not blockades but veils. And veils are not absolute, they shift, they shimmer, They sometimes let things pass through in silence. This perspective nudges us to reconsider identity. How often do we lock ourselves into rigid definitions: who we think we are, what roles we believe we must play, what futures we deem possible? Tunneling suggests that these identities are not fortresses but wave functions of the self. They extend beyond the boundaries we set. They allow us to exist in possibility, to occupy the space of maybe. The lesson here is quiet but profound. The world is more porous than we think. And so are we. The brilliance of tunneling lies not in its defiance of rules, but in its reminder that rules contain exceptions, that even strict systems have seams of uncertainty. Life, too, is riddled with such seams. The relationships we believe are broken can sometimes heal. The opportunities we assume are closed can suddenly reopen. The future we thought impossible can materialize not by force but by persistence within possibility. And perhaps the most human lesson tunneling offers is this: that strength is not always about breaking down walls but about knowing how to exist with patience beside them, trusting that probability can sometimes do the impossible. When you frame reality this way, hope ceases to be naive. It becomes a strategy grounded in physics. Even the most improbable scenarios deserve consideration because improbable is not the same as impossible. This doesn't mean one should sit idle and wait for miracles. Even in quantum mechanics, tunneling probabilities increase with proximity, repetition, and time. The longer and more consistently a wave leans against a barrier, the more likely it is to be found on the other side. Persistence, then, is not just a human virtue but a physical principle. The universe rewards presence. At its heart, tunneling is not violent. It does not shatter or conquer. It flows. It slips through cracks. It embodies a gentleness that reveals an often overlooked truth: that not all progress is loud or forceful. Some of the most profound changes arrive quietly, silently, almost imperceptibly, until suddenly the impossible has already happened. This is the grace of tunneling. It is a physics of humility. And if we apply that lesson to our own struggles, it means that the very moments we think least possible may contain the seeds of transformation. Reality itself is telling us that sometimes persistence in the space of maybe is enough. As counterintuitive as it may seem, tunneling is not an exception but a rule of the universe. It built the stars, powers our technology, and lights our path. But perhaps its greatest gift is the metaphor it lends us: that barriers are negotiable, that the improbable deserves patience, and that reality itself bends more often than we allow ourselves to believe. In the end, quantum tunneling is more than physics. It is a philosophy whispered by the smallest elements of existence, a reminder that walls are never as final as they appear, and that possibility is always, quietly, at work. Quantum randomness, where reality rolls the dice. We like to believe that the universe runs on rules. Drop a ball, it falls. Push a domino, the next one tips. For centuries, science painted reality as a chain of causes and effects, a vast mechanism whose gears always turned in predictable ways. But at the smallest scales of existence, where particles flit and flicker in quantum space, that story unravels. There, randomness isn't just noise in our equations, it is the equation. Imagine tossing a coin, not in the ordinary sense where hidden factors like wind or spin determine the outcome, but in a world where the coin itself doesn't know whether it will be heads or tails until the instant it lands. That's the strange territory of quantum mechanics, a universe where outcomes aren't written in advance, but born spontaneously in the moment. Classical physics once promised us a clockwork cosmos. Newton and his successors described a reality so orderly that, in theory, if we knew every position and momentum, we could forecast the future with absolute accuracy. Determinism ruled. Cause created effect, endlessly predictable. Yet quantum theory shattered this narrative. Its equations, especially the Born rule, which converts wave functions into measurable probabilities, don't hand us certainties, only likelihoods. A photon may go left or right, an electron may spin up or down, a radioactive atom may decay now or a billion years later. Not even the laws of physics decide in advance. The best we can do is play the odds. And this isn't a flaw in human understanding. It isn't ignorance waiting for an answer. It is reality itself refusing to be fully determined. Einstein famously balked at this, declaring, "God does not play dice with the universe." Yet experiment after experiment from Bell's inequalities to quantum erases showed that dice are indeed woven into the universe's very foundation. The randomness isn't hiding behind some curtain of hidden variables. It is intrinsic. It is unapologetic. Take radioactive decay. An unstable atom sits unchanged for ages, then suddenly spits out a particle. Why at that moment? Why not earlier? Why not later? There is no hidden trigger. The timing is a roll of quantum dice. We can only describe decay in terms of half-life, a statistical average across many atoms. For an individual atom, it's pure chance. And this chance doesn't stop at the atomic scale. The very fabric of existence bears its imprint. Chemical reactions that make life possible, the quantum fluctuations that seeded galaxies, even the flickers of noise that may underlie human thought, all are influenced by randomness at their roots. This flips our usual understanding of reality. We tend to equate randomness with chaos or meaninglessness. But what if randomness is the seed of creativity? Without unpredictability, there would be no mutation, and thus no evolution. Life itself would stagnate. Consciousness too might depend on a dash of quantum noise, a flicker of spontaneity that prevents us from being mere biological machines. In this light, randomness isn't the death of meaning, it's the birthplace of novelty. Still, the human brain resists. We are wired to find patterns. We crave causality. We build religions, sciences, and personal stories on the assumption that one thing follows another. Randomness unsettles us because it undermines control. How can we plan, predict, or prepare if some outcomes are fundamentally unknowable? Yet maybe the lesson isn't despair, but humility. Not every question has an answer. Not every outcome can be foreseen. The universe is less a machine and more a conversation, one where possibility is the language. Think of randomness as a cosmic invitation. It asks us to live without the guarantee of certainty, to step forward without knowing where we'll land. That is where human courage mirrors quantum truth. Every time we take a risk, speak an uncomfortable truth, fall in love, leave behind a familiar path, we leap into uncertainty. We don't act because the result is guaranteed. We act because the act itself matters. Randomness, then, becomes a metaphor for existence. It is the space where life breathes, adapts, evolves. A perfectly predictable world would be frozen, mechanical, sterile. But randomness opens cracks for the new to enter, for galaxies to form, for species to change, for ideas to spark. And this randomness is not chaos. It's possibility structured by probability. A casino run by the universe, where every roll of the dice reshapes reality, not by breaking rules but by playing them differently each time. Look closer, and you'll see this in your own life. Every breath, every thought is a ripple influenced by the quantum substrate beneath. Every neuron firing in your brain is nudged by probabilities, not certainties. Even the origins of the cosmos may trace back to random quantum fluctuations in a vacuum, tiny jitters that ballooned into galaxies. To dismiss randomness as disorder is to miss its beauty. It is the silence before music, the blank canvas before paint, the pause before choice. It is not the enemy of reason, but its partner, because without unpredictability, reason would have nothing new to discover. We resist uncertainty because it unsettles our need for control. But perhaps peace comes not from eliminating randomness, but from embracing it. To live as if the universe is a conversation, not a script. To accept that meaning is not given, but created in the spaces where outcomes could go many ways. In this sense, quantum randomness is both a scientific truth and a philosophical challenge. It tells us the universe doesn't fully know itself, and neither can we. Yet within that not knowing lies freedom, creativity, and growth. Randomness is the crack where possibility enters. It is the breath of novelty in a universe that might otherwise be static. And maybe, just maybe, it is the place where meaning is born. The cosmos, then, isn't a machine wound tight by laws. It is a dance of probabilities, a playground of potential, a roulette wheel spun not once but endlessly. The dice aren't in God's hands, nor ours, they're in the architecture of reality itself. And perhaps that's not something to fear, but to celebrate. Because it is in randomness, in uncertainty, in the shimmer between what is and what might be, that life happens, love happens, and reality itself unfolds. Quantum eraser. How forgetting rewrites reality. What if forgetting was not just a personal lapse but a fundamental principle of the universe? Imagine that erasing a piece of knowledge doesn't simply leave you in the dark, but actually reshapes the events that knowledge once defined. This is the bizarre, almost dreamlike implication of one of quantum physics' strangest revelations, the quantum eraser. At first glance, it sounds like science fiction: measure something, then delete the record, and suddenly it's as if the measurement never happened. But experiments have shown that the quantum world operates with a logic far more slippery and unsettling than classical cause and effect. In these experiments, photons or electrons behave like waves when unobserved, spreading out in elegant interference patterns. The moment you record which path they took, that wave vanishes and they behave like discrete particles. But here's the twist. If you later erase that which path information even after the particle has already been detected, the interference pattern can return. Somehow, the decision to remember or forget alters the story of what already happened. It's not exactly time travel, but something stranger, a universe where the past remains provisional until we decide what knowledge we keep. The quantum eraser builds on the legendary double-slit experiment, the bedrock demonstration of quantum weirdness. Fire a stream of particles through two slits and they interfere like overlapping ripples, unless you observe which slit they pass through, in which case the interference disappears. That much has been known for decades. But the quantum eraser introduces a startling twist. By entangling particles and then giving ourselves the option to preserve or erase which path data, we gain the power to decide whether the past looked wave-like or particle-like. This decision can even be delayed until after the particle has been recorded, which suggests that the universe itself waits for our bookkeeping before committing to a version of events. It's as though reality is a draft manuscript that doesn't solidify until we hit save. But let's slow down. Why does this matter beyond physics labs? Because it points toward a deeper truth. Information isn't passive. It doesn't just describe reality, it helps construct it. The act of knowing, and the choice to preserve or discard that knowledge, plays an active role in shaping what is real. Philosophically, that's earth-shaking. If the erasure of data can reinstate wave patterns as though the measurement never occurred, then the universe seems to care less about what actually happened, and more about whether we preserve the context of that happening. Think about that in human terms. When we forget, do we in some sense unmake the event? When trauma fades, when memory dissolves, is part of reality itself rewritten not metaphorically, but structurally. Here's where commentary becomes essential. The quantum eraser forces us to revisit age-old questions about memory, perception, and choice. Neuroscience tells us that human memory is malleable. Every recall alters the memory itself, blending imagination with fact. Psychology suggests forgetting is not simply loss but an active process our brains prune information to make room for survival-relevant narratives. In light of the quantum eraser, this isn't just a biological quirk. It may rhyme with the fabric of reality itself. Just as deleting quantum information restores superposition, forgetting may restore possibility, letting the mind craft new meanings unchained from the rigid script of what was. The delayed choice quantum eraser experiments conducted by physicist Yoon Ho Kim and colleagues in the 1990s showed this with dramatic clarity. Entangled photons were sent down different paths, one toward detectors that could record which path information, the other toward a device where experimenters could choose whether to preserve or erase that information. Astonishingly, when the path information was erased even after the first photon had been registered, the overall pattern showed interference. When the information was preserved, the interference vanished. It's as though the universe asked, "Do you really want to know what happened?" and only finalized the past once an answer was given. Notice what this implies. Causality is not the simple chain we assume it to be. Normally, we think of the past as fixed, the present as unfolding, and the future as open. But in the quantum eraser, the past is conditional, hanging in suspension until choices made later resolve it. Reality is not a ledger but a living document, where the margins can be erased and rewritten depending on whether information is kept. This is not merely physics, it's metaphysics with experimental evidence. From here, the philosophical questions spiral. If reality itself waits for us to decide whether to remember or forget, what does that mean for human agency? Are we co-authors of reality rather than passive witnesses? If knowing changes the system, and erasing knowledge unchanges it, then responsibility acquires new shades. Choosing to know is itself a form of intervention. Choosing not to know, choosing to erase carries weight as well. This raises haunting ethical dilemmas. If ignorance reshapes outcomes, are we morally responsible for the things we decline to learn? Does deliberate forgetting cleanse not just conscience but reality itself? Let's extend the metaphor. Picture watching a movie, but the film doesn't fully solidify until you commit the scenes to memory. Until then, the plot is provisional, the characters uncertain, the twists ambiguous. If you later discard or deny the memory, the film retroactively changes, offering a different sequence of events. That's how the quantum eraser makes reality look not like a completed narrative, but like an improvisational performance, waiting on our decisions about what matters. And what about the mind itself? Our memories are not static imprints but shifting reconstructions. Forgetting may not be failure but freedom. Just as erasing quantum information lets the interference pattern return, forgetting might let new pathways open in our personal lives. Trauma, regret, and rigid identities could dissolve, not because we rewrite them but because they lose definition when unremembered. Healing, then, could be understood not as editing the past but as erasing it, letting the narrative breathe again. This perspective reframes the idea of free will. Classical physics imagines a deterministic universe where past causes lock in future outcomes. The quantum eraser cracks open a space where the past is flexible, contingent on knowledge. In human terms, this suggests that agency is not just about making choices in the present, but about choosing which memories to keep, which knowledge to preserve. Reality is not only sculpted by what we do, but also by what we let dissolve. Skeptics argue that these interpretations go too far, that the quantum eraser is simply about correlations in data, not metaphysical freedom. But even if that's true, the implications remain staggering. Information doesn't just sit passively, it governs what patterns emerge. Deleting it changes the pattern itself. Whether we couch this in mystical terms or in sober physics, the lesson is the same. Knowledge and its erasure are active players in the unfolding of reality. Ultimately, the quantum eraser teaches us that the universe is not a stone tablet but a chalkboard. Marks can be made, erased, and remade, and the picture that remains is contingent on the choices of what we preserve. That doesn't mean we can time travel or undo our mistakes. But it does mean that the act of remembering and forgetting is woven into the fabric of existence in ways we're only beginning to grasp. You are not just a reader of reality but also its editor. Every memory you keep sharpens the image. Every memory you let fade allows a different story to emerge. The past is not gone, but neither is it fixed. It waits, ambiguously, for you to decide which version will live on. And in that space between knowing and erasing, between remembering and forgetting, lies perhaps the deepest freedom we have, the freedom to co-shape reality itself. The paradox of time. Why quantum physics allows reversals but life doesn't. Imagine standing before a perfectly calm lake at dawn, its surface so smooth that the clouds above and the water below merge into a single seamless canvas. Then you toss in a stone. Ripples spread outward, distorting the mirror image, and no matter how much you wait or wish, the lake never quite restores its original stillness. This image isn't just a poetic reflection, it captures one of the most unsettling paradoxes at the heart of physics. At the quantum level, the universe should be reversible, yet our lived world stubbornly marches forward, never back. Why? The mathematics of quantum mechanics, in its purest form, doesn't prefer past over future. Schrödinger's equation, which governs the evolution of wave functions, is entirely reversible. If you know the state of a system at a given moment, you can run the equation forward or backward to recover both future and past states. Theoretically, nothing is lost. But theory and reality rarely line up neatly. Our world, The world of melting ice, broken glass, heartbreak, and history resists reversal. Time flows in one direction, and entropy, the measure of disorder, is its arrow. This contradiction has haunted physicists, philosophers, and ordinary people alike. On paper, the universe is a stage for reversible dances of particles. In practice, however, the show unfolds only once, and there is no encore. Entropy explains much of this. Systems tend to evolve from order to disorder because disordered states vastly outnumber ordered ones. It's not that the molecules in a glass of spilled milk can't jump back into the glass. It's that the odds of them all cooperating to do so are vanishingly small, so small, in fact, that for practical purposes, it's impossible. This gap between the possible and the probable is the key to why physics whispers reversibility while reality shouts irreversibility. And yet, the quantum realm teases us with hints of reversal. Under carefully controlled conditions, researchers have used techniques like quantum error correction, Loschmidt echoes, and entanglement experiments to coax systems back into previous states. These are like tiny windows into a universe where time might fold back on itself. But they are fragile windows. Slam them shut with the noise of the outside world, and the illusion collapses. Decoherence ensures that once a quantum system interacts with its messy environment, the information leaks away irretrievably. The purity of reversibility dissolves into the chaos of macroscopic irreversibility. But what fascinates me is not just the physics, it's the philosophical implications. If the building blocks of reality can, in principle, go both forward and backward in time, why are we trapped in a one-way experience? Perhaps this divide says something profound about what it means to be human. Our memories accumulate like entropy. You can't unknow a painful truth, unhear words spoken in anger, or unfeel grief after loss. These irreversible marks on the psyche parallel the irreversible marks in the physical world. The human heart has its own kind of thermodynamics, where trust decays like unstable particles and joy disperses unless actively renewed. And yet, irreversibility is not merely a curse. Imagine if everything could be undone, every mistake erased, every consequence reversed. Life would be weightless, stripped of meaning. The permanence of time gives weight to our actions. It's because words can't be unsaid that they matter. It's because choices carve irreversible paths that responsibility and agency exist. The arrow of time turns life into a narrative, a story with beginnings, middles, and ends, not a looping equation running endlessly back and forth. Even in the grandest theaters of physics, black holes, the paradox persists. For decades, scientists believed that information swallowed by a black hole was lost forever. More recent theories suggest that information is not destroyed but preserved in some convoluted way, encoded in Hawking radiation or smeared across the event horizon like a cosmic hologram. Yet, even if it's technically preserved, the sheer complexity of retrieving it makes it practically gone. Again, we see that distinction: reversible in principle, irreversible in practice. This mirrors life. You may hold on to fragments of the past, photos, journals, scars, but they're echoes, not resurrections. The person you were before a heartbreak or a revelation cannot be retrieved. Like scrambled molecules in warm air, the experience is dispersed into something unrepeatable. That's why nostalgia is bittersweet. It's the longing for an arrangement of your life that cannot reassemble itself, no matter how much you ache for it. And yet, this forward motion is not devoid of beauty. Entropy may dissolve order, but in its wake, it allows for creativity, evolution, and transformation. Stars burn out, but their ashes seed new worlds. Ice melts, but that meltwater feeds rivers. Relationships fade, but their endings create space for reinvention. Irreversibility is not just decay, it is also the sculptor of change. So what does it mean to live in a universe built on reversible equations yet flowing irreversibly toward disorder? It means life is not a photograph but a film reel, always moving, never pausing for a retake. It means regret is inevitable but so is growth. It means that while you cannot reclaim the pristine stillness of the lake once ripples spread, you can find beauty in the dance of waves. The paradox of time is thus not a flaw of physics but a condition of existence. Quantum mechanics may hold the dream of reversibility, but the arrow of entropy grounds us in the here and now. Our lives are stories, not cycles, and their value lies precisely in their forward momentum. Every decision, every word, every ripple we create cannot be undone, and that is why they matter. So perhaps the task is not to fight irreversibility but to embrace it. To recognize that what cannot be rewound must be lived with intention. To accept that entropy writes endings but also beginnings. And to see in the permanence of time not tragedy but meaning. For in a universe where particles may dance backward and forward, it is the human experience of one-way time that gives life its depth, its urgency, and its soul. Vacuum fluctuations. How nothing creates everything. We are taught from childhood that nothing is absence, an empty box, a silent room, a void stripped of matter and meaning. Yet physics insists this intuition is wrong. The so-called emptiness of space is not stillness but agitation, not silence but a restless murmur of activity that never ceases. At the heart of modern quantum theory lies a claim both unsettling and liberating. The vacuum itself, the purest emptiness we can imagine, is alive with fluctuations, bubbling with virtual particles that exist only for a heartbeat before vanishing again. If this sounds like science fiction, it isn't. It is the unavoidable consequence of quantum field theory and one of the strangest truths science has ever revealed. To begin imagining this, picture yourself in a desert at night, utterly still, believing you are alone. Then suddenly, the ground trembles, not from wind or footsteps, but from something beneath the surface stirring in secret. That tremor is the metaphor closest to what the vacuum does, constantly rippling with energy beneath the illusion of silence. These disturbances are called vacuum fluctuations, and they reshape the way we understand the cosmos. The classical notion of a vacuum total nothingness died with the rise of quantum mechanics. Fields exist everywhere, for electrons, photons, quarks, gluons, and even when no particle is present, the field remains. Because of the Heisenberg uncertainty principle, energy and time cannot both be precisely fixed. This means the vacuum cannot have zero energy. It must seethe with motion, its lowest state called zero-point energy. That nothingness vibrates like a pond whose surface looks still but underneath, currents writhe with potential. Out of this sea, particle-antiparticle pairs emerge and annihilate almost instantly. Though fleeting, their fingerprints can be measured. The Casimir effect shows two uncharged plates in a vacuum attract each other because quantum fluctuations outside push harder than those between. The Lamb shift shows atomic energy levels nudged by vacuum activity. And the most dramatic prediction, Hawking radiation, suggests black holes evaporate as virtual pairs form at the event horizon, with one particle escaping and the other falling in. All of these phenomena reveal that the vacuum is not a passive backdrop. It is the stage, the actor, and the scriptwriter of reality. But describing the vacuum as boiling with particles risks a misunderstanding. These entities are not real in the classical sense. They don't travel paths, they don't endure. They are virtual, allowed by quantum rules to briefly exist so long as they disappear quickly enough to satisfy energy-time uncertainty. Yet their impact on forces and constants makes them as real as any permanent particle. It is a ghostly presence, a kind of cosmic background music we cannot turn off. And when we zoom out, the implications shake our understanding of origins. Some cosmologists argue that the Big Bang itself may have been triggered by a quantum fluctuation in a metastable vacuum state. If so, the universe did not need a cause in the traditional sense. No divine spark, no external trigger, just the restlessness of nothing giving birth to everything. That notion is unsettling to many, but within physics it remains one of the most compelling scenarios. Consider what this means for stability. Our atoms, molecules, even the constants of nature might not be as solid as they seem. They may be continuously shaped by the activity beneath them, like ice floating on turbulent water. The chair you sit on feels still, yet beneath it the vacuum fluctuates. The body you inhabit feels solid, yet it too is perched atop a restless foam of possibility. If reality is underpinned by fluctuations, then solidity is an illusion created by balance, not by silence. Every second, Your existence is entangled with invisible fields playing a symphony that shapes your mass, your energy, and even your perception of causality. And here is where the philosophical weight emerges. If the emptiest regions of the universe are the most alive, then mystery is not confined to cosmic edges or supernatural speculation. It sits at the foundation of reality. The line between existence and non-existence is not rigid but porous, constantly crossed by ghostly entities. It raises haunting questions. If a universe can emerge from vacuum fluctuations, then is our cosmos just one of many that flickered into being? If the vacuum itself is unstable, could it one day transition to a lower state, rewriting all of physics in an instant? Living on such a foundation is like walking across a frozen lake that creaks beneath your every step. It feels firm but hides an abyss of uncertainty. This also reframes our human place in the cosmos. You are not an independent being carved from permanent matter, but a temporary configuration of borrowed energy, an arrangement of probabilities sustained by invisible fluctuations. Like foam on a wave, you rise, shimmer briefly, and dissolve back into the sea. That realization can feel terrifying, but it also carries wonder. It means you are intimately connected to the deepest rhythms of the cosmos. The silence you hear when you close your eyes is not silence at all, but the thrum of the vacuum, too subtle for your senses but essential to your existence. Physicists wrestle with these ideas not only as abstract thought but as measurable science. Experiments probe the Casimir effect with increasing precision, confirming that the vacuum pushes back. Astronomers consider vacuum energy as a candidate for dark energy, the mysterious force accelerating cosmic expansion. Black hole evaporation through Hawking radiation, though not yet observed, remains one of the most stunning theoretical insights of modern physics. Each example underscores that the vacuum is not metaphorical poetry but physical reality. The fact that nothing can do work push plates, shift atoms, evaporate stars destroys our inherited intuition of emptiness. Yet beyond the equations, the idea reverberates into philosophy. If reality is sculpted by fluctuations, then permanence is an illusion and creation is ongoing. If black holes evaporate because of ghost particles, then even death at a cosmic scale is not absolute but transformed by hidden motion. If universes can arise from fluctuations, then perhaps creation itself is not a singular miracle but a statistical inevitability, happening endlessly across the quantum sea. And if you yourself are woven from fluctuations, then life is not separate from the vacuum but one of its most elaborate dances. What, then, does it mean to live with this knowledge? It means recognizing that certainty is a story we tell to make existence bearable. Beneath our stories lies a restless reality that does not care for permanence or solidity. But it also means that creation is more abundant than we imagined. Change can erupt from silence, novelty can emerge from nothing, and possibility never runs dry. To embrace vacuum fluctuations is to accept that the ground beneath us is not fixed but alive, and that we too are fluctuations, brief, improbable, luminous sparks in the endless foam of being. So when you stare at the night sky and feel swallowed by emptiness, remember that darkness is anything but empty. It boils, it flickers, it sings with ghostly energy. And you are part of that same restless song, a temporary crest on an eternal wave. Perhaps that is the strangest truth of all, that in a universe where even nothing cannot sit still, existence itself is the most natural fluctuation of all. The quantum debt. How reality runs on borrowed energy. Imagine walking through a city at night where every street lamp only lights up when you approach, then quickly fades back into darkness after you pass. That eerie sense of fleeting illumination mirrors what happens at the foundations of reality. Quantum mechanics allows particles to borrow energy for a moment, not permanently, but just long enough to exist, interact, and vanish without leaving behind a measurable trace. At first glance, this seems like cheating, as though the universe has loopholed its own accounting system. But in truth, it's one of the most profound features of the quantum world, where conservation laws are not broken but flexed in ways classical physics could never imagine. The heart of this strange borrowing lies in the Heisenberg uncertainty principle, not the famous version about position and momentum, but its twin principle that ties energy to time. It says the more precisely we know the energy of a system, the less precisely we can know how long it maintains that energy. Flip it around, and if something only exists for a blink of time, it can momentarily possess more energy than it should, as long as it gives it back before the universe notices. These fleeting fluctuations produce what physicists call virtual particles, particle-antiparticle pairs that constantly blink into and out of existence within the vacuum. They are invisible to direct detection, but their fingerprints are everywhere. They shift energy levels in atoms, alter the behavior of electromagnetic fields, and even influence the shape of space itself. If you think this sounds like science fiction, consider black holes. Classical physics once portrayed them as eternal prisons of matter and energy. But Stephen Hawking showed that near their horizons, quantum borrowing creates real consequences. Virtual particles pop into being. Occasionally, one escapes while the other falls into the black hole. The escaped particle becomes real radiation, Hawking radiation, while the black hole loses a tiny bit of mass. Over unimaginably long timescales, a black hole could evaporate not through violent explosions, but through quiet quantum leakage. In this sense, black holes don't just consume, they pay a cosmic tax through the mechanism of borrowed energy. Another vivid example is quantum tunneling. Classical intuition tells us a particle can't cross a barrier without enough energy to climb over it. Yet in the quantum world, particles often appear on the other side of barriers they should never surpass. It's as if they borrowed energy just long enough to sneak through, instantly repaying it upon arrival. Without this effect, the sun would not shine. Nuclear fusion inside stars relies on protons tunneling through their mutual repulsion. Even our technology, from nuclear energy to scanning tunneling microscopes, relies on this subtle bending of rules. In short, our universe wouldn't exist as we know it without the fact that particles can occasionally act as though they're operating on borrowed funds. But what's even more mind-bending is how this borrowing challenges our notions of time and causality. In our daily lives, borrowing and repayment are linear. First you take, then you return. In quantum mechanics, the sequence can blur. Virtual particles can alter real particles and vanish before the effect is fully measured. Calculations in quantum field theory often involve loops where particles interact with themselves in paths that look like they travel backward in time. Cause and effect lose their strict order. Time becomes elastic. This doesn't mean the universe is lawless, it means its laws have more nuance than our everyday sense of order. Think of it as a system of cosmic tolerances. High-energy borrowings vanish almost instantly, while lower-energy borrowings can linger a bit longer. The larger the loan, the faster it must be repaid. It's like a natural form of quantum karma. Reality allows the impossible briefly, but the debt must be cleared before the books close. The laws of physics bend, but they don't break. This flexible rulebook builds an economy of probabilities where every action can temporarily overdraw, provided balance is restored. Yet, this elegant accounting trick also hides one of modern physics' deepest puzzles, the cosmological constant problem. When physicists calculate the energy of the vacuum, the sum of all possible quantum fluctuations across space, the number is unimaginably huge, so huge it should crush the universe into nothing. But when astronomers measure the actual cosmological constant, they find a tiny value, just enough to gently accelerate cosmic expansion. Something is cancelling almost all of that vacuum energy, leaving behind only a faint whisper. It's as though the universe's ledgers are filled with astronomical borrowings that somehow balance out so well that we only see the smallest residual. Why this is so remains one of the great unsolved mysteries. On a human level, this resonates with our own psychology. We are creatures bound by rules yet drawn to exceptions. We hope for moments where debts can be made and erased without consequence, where shortcuts are allowed as long as balance is eventually restored. Quantum mechanics seems to echo that hope, not by breaking conservation laws, but by revealing their hidden flexibility. The universe seems to whisper that order isn't rigid perfection, but rather a dynamic balance where temporary chaos creates lasting structure. From another perspective, this makes our existence even more extraordinary. Every atom in your body, every firing neuron in your brain, Every beat of your heart depends on a reality stitched together by these invisible allowances. You are literally built on fluctuations, on particles that were, for a fleeting moment, almost not there at all. In a sense, you exist because the universe tolerates tiny violations that immediately self-correct. What looks to us like permanence is actually a carefully choreographed dance of impermanence. Philosophically, this challenges our ideas of permanence, cost, and consequence. We imagine the universe as a machine with strict inputs and outputs. Yet the deeper truth may be that reality functions more like a theater where improvisations are allowed, as long as the final scene aligns with the script. The particle borrows energy, leaves behind an influence, then disappears. The trace remains even though the actor is gone. It's an echo of impermanence, a reminder that certainty is not the language of the cosmos. Probability is. So, when we speak of borrowed energy, we're not talking about a minor quirk or loophole. We're describing one of the defining features of reality itself. Without these momentary deviations, black holes would never evaporate, the sun would never shine, and you would not exist. The universe is not an engine of absolutes, but a vast marketplace of temporary allowances. It is not built on unshakable certainty, but on elastic tolerances where the impossible is permitted briefly, then erased, leaving only the balance intact. Every atom, every star, every galaxy is part of this quantum economy. It is a system that flexes but never collapses, an invisible accounting where the smallest cracks in logic allow the greatest structures to exist. And at the end of the day, perhaps the most poetic truth is this: reality itself is a grand theater of borrowed light. Walking through infinite realities, the haunting beauty of the many worlds theory. Imagine standing in a corridor that stretches endlessly, lined on both sides with doors engraved with your name. Some doors glow with warmth, others appear cracked and ominous, but each represents a choice you could make. Every time you reach for a handle, the hallway behind you disappears and a new one forms ahead, populated with doors that didn't exist until that instant. This strange imagery is more than just metaphor, it captures the unsettling essence of the many worlds interpretation of quantum mechanics, a theory that suggests that every possible outcome of every decision, every quantum event, doesn't vanish, but instead splits into a new branch of reality. To grasp why this is so profound, let's step back. Classical physics tells us the world is orderly, predictable, almost mechanical. Drop an apple, it falls. Push a door, it swings open. But when scientists looked closer, down into the subatomic realm, they found chaos. Particles existing in multiple states at once, probabilities instead of certainties, cats that are both alive and dead until we peek inside the box. In the Copenhagen interpretation, observation collapses these possibilities into one. But Hugh Everett, in 1957, proposed something far more radical. What if nothing collapses at all? What if every possibility happens, each in its own universe? Suddenly, reality isn't a single line of dominoes falling, but a constantly branching tree with infinite offshoots. Now, let's think about what this means for everyday life. Every choice you make, whether to sip tea or coffee, whether to send a risky message or delete it, whether to turn left or right at a street corner, splinters reality. In one universe, you drank tea. In another, you chose coffee. Somewhere, you hit send. Somewhere else, you didn't. These aren't hypothetical scenarios in Everett's model. They are as real as this world, but sealed off, unreachable, never to interact with the version of you reading this now. The haunting twist is that these branches don't stop multiplying. Every interaction between particles, every flicker of quantum uncertainty, creates more universes. This isn't just about monumental life choices. The splitting happens constantly, whether you're conscious of it or not. The sheer scale is unimaginable, like mirrors reflecting mirrors into infinity, except each reflection is its own distinct universe. Of course, skeptics argue this is philosophical fantasy. We can't see other universes, so what does it matter if they exist? Yet the math behind many worlds is elegant. It preserves the Schrödinger equation without introducing arbitrary collapse. In fact, Everett's model solves a stubborn puzzle in physics: the role of the observer. In the Copenhagen view, consciousness almost has mystical power. Your act of observation forces reality to choose. But many worlds removes this mysticism. It says, observers don't decide outcomes, they just follow one branch. Reality doesn't collapse, it just expands. This makes the theory sound both less magical and infinitely stranger. And here's where it gets personal. The thought that there are countless versions of you, some thriving, some struggling, some living lives you can't even imagine, reshapes how we think about identity. Who are you? If every version of you exists, which one is the real you? Each branch believes itself to be authentic, narrating its story as the one true thread. But if all are equally real, then identity becomes less about uniqueness and more about perspective. You are not the whole book. You are a single page, written by a cosmic pen that never stops. This raises ethical and emotional questions. If every decision you might make is played out somewhere, what does responsibility mean? In one branch you apologized. In another you stayed silent. In one branch you chose kindness. In another you didn't. Does guilt lose meaning if, somewhere, you did the right thing? Or does that make your responsibility here even heavier, because this branch is the one you actually live through? Many find comfort in imagining unlived lives are real elsewhere. The idea that, somewhere, I made the right choice, softens regret. But it can also be crushing, knowing that for every triumph here, there are universes where you've failed miserably. Regret, pride, fate, these concepts all blur under the lens of many worlds. Still, let's not get lost in despair. Paradoxically, the theory can be deeply empowering. Yes, infinite versions of you exist, but your conscious awareness rides only one thread. You can't touch or feel the others. That makes this life, this path, profoundly meaningful. Your choices here shape the story you experience. Even if other stories are written, you are the protagonist of this one. Think of it like music. Countless melodies could exist, but the one you're hearing now is what moves you. The many worlds theory doesn't erase the sacredness of choice. If anything, it amplifies it, because each decision is the brushstroke that paints the version of life you actually get to inhabit. Interestingly, glimpses of this strange multiverse idea show up in technology. Quantum computers rely on superposition, where quantum bits exist in multiple states simultaneously. Some researchers speculate these machines might, in some sense, draw on computations across branches of the multiverse. This is controversial and not proven, but if even partly true, it means your laptop could be whispering into other worlds every time it processes quantum information. Science fiction, maybe, but today's impossibility has a habit of becoming tomorrow's discovery. The philosophical shockwaves of many worlds are immense. It challenges our sense of destiny. Fate isn't a single line stretching into the future, but a fractal of infinite paths, all walked by versions of us. Regret loses bite because no choice is final, but it also loses healing because no choice is unique. Agency isn't destroyed, but reframed. You still matter, here, now, in this world. And maybe that is all that matters. Because you won't live in those other branches. You won't feel their joys or their sorrows. You will live with the choices of this thread. So, what does this tell us about meaning? It suggests that reality is stranger, wider, deeper than we can imagine. That our lives are both tiny and infinite. That the doors we open on are all the doors we leave behind. It tells us that existence isn't about certainty, but about experience. You will never meet the you who chose differently, but you carry the memory of your own choice, and that is enough to give life texture. In this light, the many worlds theory becomes strangely tender. It reframes mistakes not as permanent scars, but as branches of growth. It reframes success not as destiny fulfilled, but as one path among infinite others. And it whispers a quiet reminder, this thread is yours. Walk it fully, choose as if it matters because it does, to you. Even if countless universes bloom from your decisions, you only breathe inside this one. And maybe that's the haunting beauty of it. In the face of infinity, the fragile present becomes infinitely precious. Entanglement swapping. The quantum secret of connection without contact. Imagine a world where relationships do not require meetings, signals, or physical touch. Instead, bonds are written into the very mathematics of reality. This is not science fiction, but the strange territory of quantum mechanics, and more specifically, a phenomenon known as entanglement swapping. To grasp its significance, we first need to step into the landscape of quantum entanglement itself, one of the most counterintuitive and experimentally verified predictions of modern physics. In the quantum world, two particles can become entangled, meaning their properties are not independent but correlated in ways that defy classical explanation. If you measure one, the other's state is immediately determined, regardless of how far apart they may be. Einstein famously described this as spooky action at a distance, because it appears to circumvent the universal speed limit of information transfer. What makes it even stranger is that these properties do not exist in a definite way until one particle is measured, at which point its partner seems to instantly decide as well. Now take that already unsettling idea and push it further. Entanglement swapping asks, can two particles that have never interacted, never shared space, still become entangled? The answer is yes, and it requires a clever trick. Suppose we start with two pairs of entangled particles, one pair labeled A and B, the other pair labeled C and D. Initially, A and B are linked, and C and D are linked. If we bring particles B and C together and perform a special joint measurement known as a Bell state measurement, we effectively entangle them. But here's the twist. As B and C link, A and D, two particles that never met, suddenly become entangled. The original connections are swapped, leaving us with a new pair of correlated particles. It is as if invisible strings were tied, cut, and reconnected without ever requiring direct contact. The implications are profound, both scientifically and philosophically. Scientifically, entanglement swapping has already been demonstrated in laboratories using photons, and it provides a roadmap for building quantum repeaters devices that will extend quantum communication across vast distances. This could pave the way for a future internet that relies on entanglement rather than signals, promising security and speed far beyond today's networks. It is also a stepping stone toward quantum teleportation, where the state of one particle can be transmitted across space by leveraging entangled connections. But what fascinates many beyond the technical applications is what this says about reality itself. In our everyday world, connection requires contact. Friends meet, signals travel through wires, and causes precede effects. The quantum world undermines this intuition by showing that relationships can exist without interaction, that correlation can take precedence over causation, and that identity itself may be defined less by substance than by linkage. Entanglement swapping embodies this paradox. Two particles, once strangers, become partners not through touch but through context, defined by their relationship through a shared intermediary. Consider what this metaphor suggests about human life. Often, our paths are shaped by people we never meet directly. A decision made by a stranger, a word passed through a mutual acquaintance, or even a historical event rippling across generations can entangle our lives with theirs. Just as particles can become correlated through an intermediary, so too do we carry unseen bonds shaped by networks of connection. Your identity, in this view, is not fixed or isolated but a node in an evolving web of relationships. Who you are is inseparable from who you affect and who affects you. Philosophically, entanglement swapping forces us to question what it means to be separate. If two particles that never touched can share a state, then the universe may not be built from isolated objects but from patterns of interrelation. What matters is not location, but correlation. Reality itself might be less like a collection of things and more like a tapestry, woven from invisible threads that link across space and time. The boundaries we imagine between self and other, here and there, cause and effect may be more porous than we realize. From another angle, entanglement swapping challenges our sense of temporality. In classical physics, cause precedes effect in a linear chain. Yet in quantum mechanics, the link between particles can be established retroactively through measurements. It is as if the future can shape the past, or at least redefine what connections exist. This opens unsettling questions. Does reality wait to be finalized by observation? Does entanglement mean that the universe is more holistic than sequential? Such questions keep philosophers and physicists equally restless. Technologically, entanglement swapping represents not just a curiosity, but a tool. Imagine a secure communication channel where messages are not sent but shared across entangled states. Unlike classical encryption, where codes can be broken, quantum entanglement offers security rooted in the laws of physics. If an outsider tries to measure or intercept the entangled system, the very act of interference changes the outcome, revealing their presence. Quantum repeaters, powered by entanglement swapping, would allow these secure channels to stretch across continents and perhaps even planets, creating a foundation for an interplanetary quantum internet. And yet, the wonder of entanglement swapping is not just in the future it promises, but in the present reality it exposes. At its core, it tells us that the void between things is not empty. Space itself is charged with potential links, with correlations waiting to be discovered. Even absence can be a medium of connection. This challenges us to rethink how we view separation, both in physics and in our lives. Perhaps distance, whether physical or emotional, does not sever connection as completely as we assume. The unseen ties may still remain, waiting for the right context to reveal themselves. Ultimately, entanglement swapping is a scientific phenomenon with philosophical resonance. It suggests that the universe is not merely a stage of objects bumping into one another, but a web of relationships where context and correlation take center stage. And within that framework, perhaps we, too, are more than isolated beings. We are participants in an ongoing conversation, part of a cosmic network where every choice and connection reverberates through unseen channels. Just as two particles can become entangled without meeting, so too can our lives be shaped by influences that never touch us directly. This is why entanglement swapping feels almost mystical, even though it is grounded in rigorous science. It shows us a cosmos where connection is deeper than contact, where information flows through invisible harmonies, and where the fabric of reality itself is stitched together by correlations rather than collisions. In the end, it may be less important to ask where a particle is or what it is, and more important to ask, what is it connected to? That, perhaps, is the true signature of existence. Entanglement swapping teaches us a lesson that extends far beyond quantum labs, that separation is not absolute, that unseen links bind us across space and time, and that reality is richer and more interconnected than we dare to imagine. It is both a key to future technology and a mirror reflecting back at us the hidden nature of connection. And maybe the most beautiful truth is this: in a universe where even particles that never meet can share a bond, perhaps none of us are ever truly alone. The silent symphony, why quantum fields are the true reality. For centuries, humans have been trying to peel back the layers of reality, like archaeologists digging through the ruins of existence, convinced that at the very bottom we'd find the smallest, most unbreakable brick of the universe. At first, it was the atom, the so-called indivisible particle. Then came the discovery of electrons, protons, and neutrons, which turned the indivisible into a divisible puzzle. Later, scientists uncovered quarks, leptons, and bosons, tiny actors in a cosmic play. For a long time, the dominant metaphor was that of Lego blocks, solid, miniature beads of matter drifting in the vast emptiness of space, colliding, clumping, and constructing the stars, planets, and everything we see. But modern physics has demolished this Lego set picture. Instead, it offers something far stranger, more beautiful, and more unsettling: the idea that particles are not fundamental at all. They are not the bricks but the ripples. Beneath every particle lies something deeper, more universal, more omnipresent: quantum fields. Imagine standing in an empty theater long after the performance is over. The actors are gone, the lights are off, and yet, you can still sense something intangible in the air, a lingering presence of the play. Fields are like that, always there, always humming, regardless of whether the actors' particles are currently on stage. These fields are not confined to one location. They extend everywhere, across the entire cosmos, invisible yet unavoidable. The electron field stretches through you, me, the stars, and the void between galaxies. The electromagnetic field, the gluon field, the Higgs field, they are all stitched into the very fabric of space. To exist in this universe is to be immersed in them. So what is a particle, then? not a thing in itself but a fleeting event. An electron is not a permanent pebble but a vibration in the electron field. A photon is not a tiny bead of light but a pulse in the electromagnetic field. Each particle is like a note played on an instrument, a brief song that echoes and fades, while the instrument itself, the field, remains. When the note stops, the field doesn't vanish. It is eternal, silent, ready to play again. This flips our intuition upside down. We are used to thinking of emptiness as nothingness, a void stripped of all content. But quantum field theory says otherwise. Even the most perfect vacuum is alive with energy. Fields never turn off. Even when nothing is present, they ripple, fluctuate, and jitter with constant activity. These fluctuations, known as vacuum fluctuations, can pop virtual particles into and out of existence. And these aren't hypothetical experiments confirm them. They shift atomic energy levels, create forces between objects, and even leave measurable traces in phenomena like the Casimir effect. In other words, the emptiness we imagine is actually a restless ocean, and the waves of that ocean are what we mistake for matter. Now, why do we perceive the world as made of solid particles rather than these elusive, invisible fields? Because our instruments, including our eyes and our brains, only register the events, the collisions, the strikes, the interactions where fields ripple hard enough to leave an imprint. What we call a particle is simply the footprint of a field touching us, not the field itself. Like someone watching the tip of an iceberg and assuming it's a floating stone, we miss the vast hidden mass beneath. The reality beneath the particle is continuous, seamless, unbroken. And the beauty of this framework is that it explains not just matter but also the forces of nature. The electromagnetic force, that's the photon field at work. The strong force that binds quarks together, that's gluons rippling in their field. The weak force, which governs radioactive decay, that comes from W and Z boson fields. Even the Higgs boson, discovered only in 2012, is just a vibration in the Higgs field, a field that pervades the entire cosmos and gives mass to particles. Without it, electrons would have no weight, atoms would never form, and the universe would collapse into featureless chaos. Fields are not passive stages on which matter performs, they are the playwrights, the architects, the invisible conductors orchestrating the whole show. And then there's the question of identity. What does it mean to be you, if the particles in your body are not permanent entities but recurring ripples of universal fields? The electron in your fingertip is indistinguishable from one in a star a billion light years away, because both are excitations of the same underlying field. Separation, individuality, boundaries, all of these dissolve under the field perspective. You are not a sealed container of matter but a temporary arrangement of waves. Your existence is less like a statue and more like a melody. When you die, the particles that made up your body will rearrange, but the fields remain. The song may end, but the instrument is still there, ready for new notes to emerge. This perspective also helps untangle one of physics' strangest puzzles, quantum entanglement. When two particles are entangled, their behaviors remain linked even across vast distances. It seems magical, almost spooky, but under the field view, it makes perfect sense. They are not truly separate entities but synchronized ripples of the same field. What looks like instantaneous connection is just the natural coherence of a unified medium. And here's where philosophy collides with physics. If everything we perceive, your body, this screen, the stars, is just a fleeting arrangement of waves in fields, what does it mean to exist? Are we things, or are we processes? Are we beings, or are we events? The field picture suggests the latter. We are patterns, temporary harmonies in a grand cosmic symphony. Matter is not fundamental. Energy is not fundamental. The deepest truth, as far as physics can see, is fields universal, eternal, inseparable. This realization is both haunting and comforting. It erases the notion of isolation. When you move your hand, you ripple countless fields. When you think, your neurons trigger electromagnetic fields. You are not cut off from the universe. You are woven into its fabric, a participant in its endless vibration. The boundaries between you and everything else are convenient illusions. At the deepest level, we are all waves in the same sea. And perhaps this is the lesson hidden within modern physics, to shift our mindset from seeing the universe as a warehouse of things to seeing it as a living song of interactions. The flicker of a candle, the shimmer of heat, the pulse of a heartbeat, all of them are verses in the same infinite hymn. Reality isn't a pile of bricks, it's a resonance, a rhythm, a silent symphony that never ceases. And we are not observers of this music. We are part of it. We are instruments playing its song. So when you look around at a mountain, a tree, or even your reflection in a mirror, remember this. What you are seeing is not solid matter but fleeting ripples of invisible fields. Beneath the noise, beneath the chaos, there is a hum that never fades. That hum is the real stage, the real reality, the canvas upon which everything is drawn. Fields are not what lies behind the curtain of the universe, they are the curtain, the stage, and the performance itself. In the end, perhaps reality has never been about things at all. It has always been about movement, interaction, resonance. You are not a collection of particles. You are a wave, a note in the timeless music of the cosmos. And once you grasp it, you may realize that the universe is not a machine, not a structure, but a living field humming infinite possibilities into being. The quantum Zeno effect, how watching too closely freezes reality. Imagine staring at a flame. Normally, it flickers, bends, and eventually burns itself out. But what if, under your gaze, the flame refused to move at all? No swaying, no dancing, no melting of wax, just a suspended fire, locked in a frozen moment. It feels like a metaphor, a piece of poetic imagination, yet in quantum physics this strange possibility has a real name, the quantum Zeno effect. It suggests that observing something too intently can halt its natural progression, as though the act of looking exerts a hidden form of control. At first glance, this seems absurd. Observation feels passive, like watching a clock tick or clouds drift. But at the quantum scale, measurement is invasive. When you examine a system, you don't simply gather information, you interfere with it. The quantum Zeno effect reveals that continuous measurement can trap a particle in its present state, preventing it from evolving. A radioactive atom expected to decay might remain suspended, undecayed, as long as it is constantly monitored. This isn't science fiction, it has been demonstrated in labs. Scientists have delayed atomic transitions by bombarding particles with frequent laser pulses, effectively asking them over and over, "Have you changed yet?" And as long as the questioning continues, the change does not occur. To understand why, we must revisit how quantum systems behave. Unlike classical objects, particles do not follow predictable paths. Instead, they exist in a haze of probabilities described by the wave function. Left undisturbed, this probability cloud spreads and evolves smoothly over time, like a musical score unfolding toward its crescendo. But when we measure the system, we collapse the cloud into a single outcome, forcing the particle to occupy a definite state. Measurement is like striking a key on the piano and freezing the song before it has a chance to play out. Do this occasionally, and the music resumes. Do it relentlessly, and the melody never starts. The philosophical weight of this effect is staggering. Ancient thinker Zeno of Elea crafted paradoxes to challenge the notion of motion, such as the famous argument that an arrow in flight is motionless at every instant of time. Quantum mechanics has made those riddles more than intellectual games. They manifest in the lab. When we observe a system too often, it resists motion, echoing Zeno's ancient suspicion that attention itself distorts reality. And this invites unsettling questions. If awareness can reshape the evolution of atoms, could our own human tendencies towards scrutiny, analysis, and over-attention have similar effects in life outside the lab? Consider personal growth. Many of us check in constantly on whether we're changing. Am I happier yet? Have I healed? Am I improving? The more frequently we measure ourselves, the more we risk freezing in place. Just as the particle resists evolution under observation, the self resists transformation under obsessive self-monitoring. Healing requires time. Creativity needs space. Growth thrives in silence, not in perpetual evaluation. Ask the wound every hour if it has closed, and it never does. Measure your happiness every day, and joy becomes brittle. The metaphor expands further in relationships. A romance scrutinized too harshly, constantly measured, analyzed, questioned becomes fragile. It can no longer breathe. Love flourishes in presence, but suffocates under inspection. Trust, like quantum evolution, requires letting go. Similarly, societies that impose relentless surveillance through cameras, algorithms, or bureaucratic oversight often discover that the very behaviors they want to nurture instead wither. Citizens under constant watch begin to self-censor. Innovation stagnates because risk-taking feels dangerous. The culture performs safety rather than living change. Like a quantum particle, society freezes when illuminated too harshly. But the quantum Zeno effect isn't merely a warning against over-scrutiny. It also reveals something profound about the role of consciousness itself. If observation changes reality at the smallest scales, then awareness might not be as passive as we assume. It might be creative, shaping, participatory. Our gaze matters. Our presence alters outcomes. Yet this power is double-edged. Attention can either nourish or imprison, depending on how it is wielded. Mindful presence is different from obsessive measurement. The former allows a process to unfold while honoring it with awareness. The latter interrupts, resets, and stalls evolution. Think about time itself. We assume time flows independently of us, like a river indifferent to its passengers. But the quantum Zeno effect suggests time may be relational. If a system pauses its evolution whenever observed, then time in that system bends around attention. Time isn't merely what clocks report. It is what the universe becomes when left to unfold. When we interrogate it too frequently, we fracture its rhythm. This reframes the old saying, "A watched pot never boils." Perhaps it's not just impatience. Perhaps attention really does interfere with becoming. Psychology reflects this as well. Overthinking is the cognitive version of quantum paralysis. The more you dissect a decision, the harder it becomes to act. The future freezes under the glare of analysis. Healing, growth, art, even love each requires some degree of unobserved space. In mystery, things evolve. In silence, wounds close. In darkness, seeds sprout. The paradox is clear. We crave certainty, but in chasing it too aggressively, we rob ourselves of transformation. Yet this doesn't mean observation is bad. It means observation must be balanced. Presence can be powerful when it is gentle. When we watch without the demand for immediate answers, we allow life to breathe. Mindfulness, unlike obsession, does not freeze. It nurtures. In fact, some experiments suggest that the quantum Zeno effect can be reversed. Under certain conditions, rapid measurement accelerates change, a phenomenon called the anti-Zeno effect. This duality mirrors life. Attention can either stall or catalyze, depending on how it is applied. The lesson, then, is one of wisdom. Learn when to look and when to step back. Learn when your attention heals and when it hinders. Just as scientists carefully time their measurements to allow systems to evolve naturally, we must pace our own awareness. Not every process requires an audience. Not every state demands inspection. Sometimes, the greatest gift you can give is trust. Trust in time, in emergence, in rhythms that unfold without surveillance. In 2001, physicists demonstrated this power by using laser pulses to prevent atoms from decaying. Each pulse was like a question. Have you changed yet? And the atoms, constantly interrupted, remained suspended. Their natural story was postponed, not by barriers of matter, but by information itself. This is staggering. Knowledge is not neutral. The act of seeking it alters the reality it hopes to capture. The observer, therefore, is not a recorder of history but a co-author of it. In human terms, this means that our awareness is never just watching. It is sculpting. It is choosing which timelines can unfold. What does this mean for how we live? It means that freedom often requires not looking. Growth needs space. Creativity thrives in moments unmeasured. Love deepens in trust. Even time itself may stretch or compress depending on whether we demand constant answers from it. The quantum Zeno effect, then, is more than a scientific curiosity. It is a mirror for our era of hyper-awareness. In a world where everything is tracked, quantified, and analyzed, we risk freezing ourselves in stasis. Progress becomes performance. Innovation mimics stability, and beneath the bright light of scrutiny, potential quietly withers. The cure is deceptively simple. It is trust. Trust in the unseen processes of becoming. Trust that not every step requires a witness. Trust that mystery is not the enemy of growth but its soil. To live fully is to balance presence with patience, attention with allowance. The quantum Zeno effect whispers a warning and an invitation. Watch wisely, or you may freeze the very life you long to see unfold. Quantum tunneling through time. When the past and future collide. What if the past isn't locked behind us, but folds beside us, waiting to be touched, reshaped, or rewritten? Quantum physics hints that this might not just be poetic speculation but a mathematical reality. At the heart of this lies a strange but well-established principle: quantum tunneling. In classical physics, barriers are absolute. A marble cannot simply appear on the other side of a wall without crossing it. Yet in the quantum domain, particles routinely do just that. Their wave functions extend beyond the barrier, seeping into forbidden regions, and occasionally manifesting on the other side as though the impossible were ordinary. This phenomenon has been experimentally confirmed countless times, shaping technologies like quantum computing and tunneling microscopes. But when physicists extend the math of tunneling into relativistic domains, where particles move close to light speed and space-time itself bends, a startling implication emerges. Particles might not only cross spatial boundaries, but temporal ones. The possibility of slipping backward in time is encoded not in science fiction but in equations that work. In the 1940s, Richard Feynman stumbled upon an interpretation that shocked even seasoned physicists. He suggested that positrons, the antimatter counterparts of electrons, could be understood as electrons traveling backward in time. This wasn't metaphor. Within his elegant diagrams, arrows could point both ways in time, and the math still predicted experimental results perfectly. Time, in this framework, lost its sacred direction. An electron moving forward and a positron moving backward might simply be two ways of perceiving the same entity. This symmetry, subtle but profound, reframed how we think of causality. Instead of time as a rigid river flowing in one direction, it began to resemble a tangled web of loops and folds. But what does it mean to tunnel backward in time? Traditionally, we assume the past is fixed and the future is open. Yet in the quantum realm, nothing is truly set until observed. Events exist as probabilities, superpositions awaiting collapse. And in rare conditions, quantum fluctuations allow particles to briefly defy conservation laws, borrowing energy or momentum so long as the debt is repaid almost instantly. These fleeting apparitions are called virtual particles. From one perspective, they are harmless quantum noise. From another, when mapped onto Feynman's formalism, they resemble particles darting backward in time before correcting course. The symmetry demands it. Without this allowance, the math breaks down. This cracks open a philosophical abyss. If fundamental building blocks of matter are free to dip into the past, does causality itself emerge only statistically, as an average outcome of chaotic negotiations where some processes run forward and others backward? Perhaps the arrow of time, so intuitive in daily life, is not fundamental but emergent. Entropy, the gradual slide from order to disorder, explains why broken cups don't reassemble and why we remember yesterday but not tomorrow. But entropy is a large-scale principle. At the quantum level, particles do not play by its rules. Time there may be reversible, and tunneling into the past is not forbidden but expected. Consider the delayed choice quantum eraser experiment. In this setup, a decision made in the present appears to retroactively determine how a photon behaved in the past, whether it traveled as a particle or wave. This isn't fantasy. It has been performed, measured, and peer-reviewed. What seems like a choice, now, reaches backward, altering what, then, must have been. The implication is staggering. The act of measurement doesn't merely uncover reality, it constructs it, even across time. Our notion of chronology, stretched to breaking, begins to snap. If we accept this, time stops being a line. It becomes a dialogue, an ongoing negotiation between states of being. Past, present, and future entangle like threads woven in no particular order, forming patterns that only appear linear to minds evolved to survive in a macroscopic world. Particles, then, are not just travelers of space, but couriers across time, ferrying information from now to then and back again. The idea isn't a Hollywood fantasy of phone booths or DeLoreans. It is the subtle, statistical twitch of time's arrow, an occasional hiccup in the otherwise forward march of entropy. What does this mean for us? If the past isn't as closed as we assume, memory itself might not be a mere archive but a living dialogue with time. Perhaps déjà vu isn't just a brain glitch, but an echo of probabilities where the future brushes against what we call before. Maybe intuition, sudden inspiration, or unexplainable foresight are not anomalies but the result of consciousness being sensitive to information bleeding backward through quantum cracks. The very notion of identity becomes fluid. Are you only the sum of your history, or are you also shaped by futures not yet played out? If so, your present self is a sculptor working not just on tomorrow, but retroactively reworking yesterday, subtly rewriting the story of who you were. The implications extend beyond philosophy. Imagine communication systems that exploit retrocausal effects, transmitting information backward across microscopic scales. Though such technology is speculative, the mathematics underpinning it isn't fantasy. It's written into quantum electrodynamics, a theory tested to extreme precision. Skeptics rightly argue that macroscopic backward causation is unlikely. Thermodynamics and decoherence prevent large-scale violations of causality. But even microscopic exceptions demand we rethink what time is. Is it fundamental, or is it emergent? Does it exist independently, or is it a statistical illusion created by entropy and observation? The deeper we look, the stranger it becomes. In cosmology, some models suggest that the Big Bang itself may have birthed not just our universe, but a mirror one, where time flows in the opposite direction. From that perspective, backward tunneling at the particle scale may be a microcosm of a cosmic truth. Time is not singular but dual, perhaps even plural, with arrows pointing both ways. Our universe, with its forward arrow, might simply be half the story. And then comes the unsettling question. If causality is flexible, how do we define free will? If the future can influence the past, are choices predetermined, or are they co-authored by events that haven't yet occurred? Perhaps free will isn't about making decisions in a vacuum, but participating in a feedback loop where decisions ripple in both temporal directions. The word you almost said yesterday might still echo in a timeline you cannot see. The decision you will make tomorrow might already be reshaping the memories you hold today. When physicists say particles can tunnel backward in time, they aren't invoking fantasy. They are following equations to their logical conclusion. The math is sober, unromantic, and precise. And yet, its implications unravel our deepest assumptions. The arrow of time, so deeply ingrained in human thought, may be less a cosmic law and more a perceptual crutch. The universe may be alive with time loops, retrocausal ripples, and feedbacks that stitch past and future together in ways we barely glimpse. So pause and let this settle. A particle detected before it is emitted. A cause preceded by its effect. A measurement reaching back to sculpt an earlier state. These aren't impossibilities but mathematical necessities. The question is not whether the universe allows them but how much of that hidden dance leaks into the reality we inhabit. If so, then memory, intuition, déjà vu, and even imagination might not be quirks of biology but side effects of existing in a cosmos where past and future are entangled. Consciousness could be more than a passenger on time's arrow, it might be the bridge across its folds, weaving continuity out of probabilities that loop both ways. And if particles can tunnel backward in time, perhaps so too can ideas, emotions, and choices. What if the past is not gone but pliable? What if every instant is both an echo of what was and a whisper of what will be? In the end, quantum tunneling backward in time is more than a curiosity. It's a doorway into a universe far stranger, less stable, and more alive than we dared to imagine. It challenges us to see time not as a one-way track, but as a living fabric, folded and rippling, where every step forward is also a drift sideways, backward, and beyond. The universe is a wave of possibility, living in a quantum multiverse. Imagine standing in front of a mirror so vast that it doesn't simply show you, it shows every version of you that could ever exist. The you who took the risk, the you who walked away, the you who stayed silent, and the you who spoke up. Each one equally real, all existing at once, waiting to be acknowledged. Now imagine that mirror isn't reflecting just you, but the entire cosmos, shimmering with possibilities not yet chosen. This isn't a piece of science fiction. It's the unsettling yet elegant suggestion born from one of the deepest puzzles in physics, that the universe itself may not be fixed, but suspended in a wave of probabilities. To understand why some physicists take this idea seriously, we have to revisit the foundations of quantum mechanics. At its core, quantum mechanics tells us that particles like electrons, photons, and atoms don't exist in definite states until they're observed. Instead, they're represented by a mathematical object called a wave function, a probability cloud describing all possible states. This wave function doesn't just float around aimlessly, it evolves predictably according to Schrödinger's equation, almost like an algorithm unfolding over time. On paper, it's neat, clean, and deterministic. But the strangeness enters when we measure. Once an observation occurs, the wave function collapses, the cloud condenses into a definite outcome, and everything else evaporates. Here's where the mystery deepens. If the building blocks of matter behave this way, then why wouldn't larger systems, molecules, brains, planets, even galaxies be subject to the same rule? Hugh Everett thought so. In the 1950s, he challenged the assumption that wave functions collapse. Instead, he proposed that they never collapse at all. Rather, every possible outcome of a quantum event happens, just not in the same universe. Each possibility unfolds in a separate branch of reality. You flip a coin. In one branch it's heads, in another it's tails, in another the coin never lands. Everett's vision, known as the many worlds interpretation, describes reality as a cosmic branching tree that never stops splitting. It's unsettling, yes, but it also elegantly avoids the weirdness of collapse. But let's pause here, because it's easy to get swept into the sci-fi allure of infinite universes. What does this idea actually mean for us? First, it challenges the way we see reality itself. We think of the present as solid and the past as fixed. Yet if the universe is fundamentally a wave of possibilities, then the present moment is simply one slice of an immense superposition. The past and future aren't neatly behind or ahead. They may coexist in a grander structure, a kind of cosmic symphony of harmonics where timelines overlap. Now, here's where personal commentary is necessary. This isn't just abstract physics, it's philosophy, psychology, even spirituality disguised in mathematics. If reality is branching endlessly, then your choices are not simply linear events, but points of divergence creating countless other versions of you. Every what if you've ever pondered isn't just fantasy. It's encoded into the structure of existence itself. You are both the author and the echo of infinite storylines. But there's an even stranger implication, the role of consciousness. In traditional quantum mechanics, observation causes collapse. But if Everett is correct and there is no collapse, then what role does observation really play? Some physicists, like John Wheeler, argued that consciousness is not a passive witness, but an active co-creator of reality. This view is called the participatory anthropic principle. In plain language, it suggests the universe requires observers to exist in the form we recognize. Think about that reality as a mirror that not only reflects us, but also needs us to complete itself. That turns the cold, mechanical image of the cosmos on its head. The universe becomes a partnership, a feedback loop where mind and matter entangle. Skeptics will point out that the wave function is a mathematical abstraction, not something tangible. You can't hold it in your hand. Yet the predictions it provides are astonishingly accurate. Experiments have shown atoms existing in two places at once, particles entangled across light years, and delayed choice experiments where actions in the present seem to influence outcomes in the past. These results don't prove many worlds, but they do show us that the universe doesn't behave like our everyday intuition expects. Every experiment confirms, Reality at its core is probabilistic, not absolute. So what does this mean for how we live our lives? If the universe is a wave of possibility, then certainty is a kind of illusion. The stories we tell ourselves about who we are and where we're going are simplifications of a much more fluid reality. It doesn't mean that nothing matters, it means everything matters more. Every decision we make is not just a small step forward, but a quantum branching, a ripple into infinite realities. Your actions are both local and cosmic, both personal and universal. Here's a personal reflection. Many people feel trapped by regret, as if the past is set in stone. But under this interpretation, every regret is just one thread among countless alternatives that continue to exist. The you who made a different choice is still out there, living that path. This isn't meant to encourage escapism, but to highlight the richness of existence. You're not confined to a single script. You are participating in a cosmic branching play where all outcomes are written, and your awareness collapses one of them into focus. At the same time, this view demands humility. If reality is fundamentally uncertain and probabilistic, then no human mind can fully grasp it. We can only ever experience the branch we inhabit. That limitation should foster wonder rather than despair. The uncertainty of existence is not a flaw. It's a feature that allows for creativity, freedom, and discovery. If everything were predetermined, there would be no room for possibility. But because the universe is a wave of probabilities, every moment is alive with potential. And so, the wave function is not just a sterile mathematical ghost, it is poetry written into physics. A reminder that reality is not frozen but flowing, not fixed but alive. Our consciousness, our choices, our observations, all of these are threads entangled with the stars, shaping and being shaped by the infinite tapestry of existence. When we step back, we realize the universe is not a machine indifferent to us. It is a field of possibility in which we are both participant and participant observed. Every thought, every gaze, every breath, is not trivial, it is an act of collapse, a moment of creation, a crystallization of one branch among countless others. This transforms how we see our place in the cosmos. We are not insignificant specks drifting in an uncaring void. We are conscious agents entangled with the fundamental fabric of reality. So the next time you question your place in the universe, remember this: you're not navigating a single, predetermined timeline. You are surfing a wave of possibility. The universe is not merely something you live in, it is something you help bring into focus. Reality is not just what you witness, it is what you co-create. Reality without particles, the universe as pure interaction. We are taught from childhood that the world is made of things. Chairs, rocks, bodies, stars, all supposedly built from indivisible pieces called particles. Tiny marbles bouncing in an invisible void, coming together to form the solidity we lean on, the matter we touch, the ground beneath our feet. It sounds straightforward, comforting even. A Lego-like cosmos assembled from discrete bricks of existence. But modern physics whispers something far stranger, something deeply unsettling and profoundly beautiful, that what we call particles may not exist in the way we imagine at all. Instead of a universe constructed from objects, the deeper truth may be that only interactions are real. Imagine a room full of people standing silently, not moving, not acknowledging each other. You might assume the room is empty of meaning until suddenly two people lock eyes, or one reaches out to shake another's hand. In that instant of contact, something emerges: connection, reality, presence. Before that, there was only potential. In a similar way, the universe may not consist of fixed objects waiting passively to be noticed, but of relationships that flare into being only when interaction occurs. At the heart of quantum field theory, the reigning framework of modern physics, a particle is not a self-contained bead traveling through space. Instead, it is a ripple, a fleeting disturbance in a field that pervades the entire cosmos. The electron field stretches everywhere, and what we call an electron is nothing more than a localized vibration of that field, something that only becomes meaningful when it exchanges energy, when it collides, when it interacts. Without interaction, it is undefined. Without measurement, it is nowhere. This shift in perspective changes everything. It means that what we experience as matter is not a set of tiny billiard balls clacking together, but the visible imprint of invisible dances between fields. The standard model of particle physics, our most accurate scientific description of reality, doesn't actually describe particles as little objects with intrinsic identities. Instead, it describes how fields exchange force, how excitations emerge, how events unfold. Feynman diagrams, the squiggly lines physicists use to calculate quantum processes, are not maps of particles traveling through space. They are diagrams of interactions: an electron emitting a photon, a quark exchanging a gluon, a neutrino bumping into a neutron. The story is always about relationships, never about isolated things. The implications ripple far beyond physics. If nothing exists as a standalone object, then identity itself must also be relational. You are not simply a body that exists independently. You are an intricate web of chemical, biological, neurological interactions. Your heartbeat is a rhythm of molecular signals. Your thoughts emerge from networks of neurons exchanging electrical pulses. Even your sense of self, your I, is not a solid entity floating in your skull. It is a process, an ongoing chorus of brain regions harmonizing perception, memory, and reflection. Consciousness, in this view, is not a particle hidden in the mind, but an emergent phenomenon born of interaction between systems. This challenges our deepest intuitions. Human beings crave substance. We want things to hold still, to be solid, to endure. We want the universe to be built from bricks, not from whispers. But at the quantum level, solidity dissolves. Try to pin down an electron's position, and it evaporates into probability. Try to isolate a quark, and it slips behind a curtain of uncertainty. Particles refuse to reveal themselves alone because alone may be a fiction. Reality does not offer us objects to observe, it offers us events, collaborations, co-creations between observer and observed. Even space and time, which we often take as the fixed stage upon which the cosmic play unfolds, may themselves be products of interaction. Research into quantum gravity and entanglement suggests that space-time could emerge from networks of quantum relationships, from webs of entangled states. If so, then, where, and when, are not fundamental coordinates, but the outcomes of deeper connections. Reality, in this sense, is not a sculpture frozen in marble. It is a conversation, a wave crashing and reforming, a dance of verbs rather than nouns. What does this mean for us, ordinary beings trying to live and understand our place in the cosmos? It means our lives, too, are woven from interactions. Love is not a thing, but an ongoing resonance between people. Memory is not a static object in your brain, but a pattern that rewires itself each time you recall it. Existence itself is participation, a continual shaping and being shaped. To be alive is not to endure as a fixed entity, but to constantly exchange energy, attention, and influence with the world around you. Think of looking up at the night sky. The starlight that meets your eyes began its journey long before humans existed. But you are not seeing a thing called a star. You are experiencing an interaction. Photons emitted millions of years ago traveling across space, colliding with molecules in your retina, triggering signals in your brain that generate the experience of starlight. You are not witnessing objects from afar. You are entering into ancient conversations carried across the cosmos. This reframing can feel almost spiritual, yet it remains rigorously scientific. Quantum electrodynamics, our most precise theory, predicts particle interactions with astonishing accuracy measured to many decimal places. And it does so not by describing particles as things, but by calculating how they interact. Physics confirms, with extraordinary precision, that what matters is not the players but the interplay. The philosophical consequences are staggering. If nothing possesses intrinsic identity, then perhaps existence itself is not about being, but about doing. You are not what you are. You are what you enact, what you influence, how you relate. Objects are illusions, snapshots of processes frozen in our perception. The universe, in this sense, is not built of bricks but of bridges, temporary connections that flare into existence long enough for something to happen before dissolving again. This perspective dissolves the boundary between science and experience. The same principle that explains why electrons are excitations of fields can also illuminate why human identity is emergent, why society functions through relationships, why meaning arises only in exchange. Life, thought, and consciousness are not isolated possessions but relational phenomena. And so perhaps we should stop asking, what is the universe made of? And instead ask, what does the universe do? Reality is an unfolding verb, not a static noun. To exist is to interact, to touch, to collide, to exchange, to relate. Without those moments of contact, there is nothing, only silence waiting for sound. When you zoom in close enough, the solidity of matter fades. What remains are patterns of energy rippling, colliding, vibrating in vast fields that extend through space and time. You, me, the stars, the galaxies, we are not things suspended in the void. We are moments in a cosmic dialogue, voices in an endless chorus of interaction. The universe does not ask you what you are. It asks how you respond when it reaches out, when it whispers your name in the ripple of a field. The no-cloning theorem, why quantum reality refuses to be duplicated. In the everyday world, duplication feels natural. We copy files, save photographs, stream movies endlessly, and back up every detail of our digital lives without a second thought. Our culture is built on replication. Yet, beneath this convenience lies a strange frontier where duplication fails completely. The quantum world, the very foundation of reality, enforces a strict rule. Some things cannot be cloned, not because of technology's limits, but because the laws of physics forbid it. This is known as the no-cloning theorem, and it overturns the very idea of copying that modern society takes for granted. Imagine walking into a library that houses every possible thought, emotion, and fragment of consciousness. Each book is a living state, suspended in potential, unreadable until opened. Now, if you tried to make a perfect duplicate of one of these books, you would expect technology to comply, just as printers churn out endless paperbacks. But in this library of reality, the moment you attempt to duplicate, the text resists. The book fades, the letters distort, and the very essence of the story refuses to appear twice. The universe itself seems to intervene, not out of mystery, but because it operates under a rule deeper than human convenience. Quantum states cannot be cloned. At its heart, quantum information is not like the words in a document or the notes in a song. It is alive, singular, fragile, and irreplaceable. This uniqueness is not an accident but a law of physics that demands respect. The no-cloning theorem, first formalized in 1982 by Wouters and Zurich, emerges from the mathematics of quantum mechanics. Its proof is surprisingly simple. If cloning were possible, it would violate the linear evolution dictated by Schrödinger's equation, the equation that drives the quantum world. Any attempt to replicate an unknown quantum state collapses its delicate superpositions, destroying the very thing one hopes to preserve. To observe is to interfere, and to measure is to change. Unlike classical information, which can be duplicated endlessly without cost, quantum information demands authenticity. To grasp this more intuitively, think of trying to copy a snowflake with your bare hands. The moment you touch it, the intricate pattern melts away. Even a camera flash alters its form. You can describe it, approximate it, simulate it, but the true identity of that snowflake remains unrepeatable. That is the reality of quantum information. It resists cloning because cloning would strip away its soul. The implications are enormous. One of the most important applications is in quantum cryptography. In classical encryption, security comes from complex math problems that can, in principle, be cracked. In the quantum realm, however, security is enforced by physics itself. If someone tries to intercept and copy a quantum key, their intrusion inevitably disturbs the state, alerting both sender and receiver. It's as if messages are wrapped in glass that shatters at the first sign of tampering. This isn't just clever engineering, it's a direct consequence of the no-cloning theorem. The impossibility of duplication also reshapes our understanding of teleportation. Science fiction imagines teleportation as a machine that makes endless perfect copies of you across the universe. But quantum teleportation works differently. When a particle's state is teleported to another, the original is destroyed. You cannot exist in two places at once. The transfer is exact but singular. Entanglement enables this fragile bridge, but cloning remains forbidden. Instead of producing duplicates, teleportation acts as a translation, moving the essence of the particle across space by erasing it from where it began. This principle also challenges how we think about building quantum computers. Classical computers rely on redundancy. Files are backed up, errors corrected with duplicates, and systems made reliable through replication. In the quantum world, redundancy cannot exist in the same way. Engineers must invent entirely new forms of error correction, using clever entanglement strategies and even exotic topological methods that encode information in braids and twists rather than direct duplication. Quantum computing is not just classical computing with more power, it is a completely new architecture built around the impossibility of cloning. Beyond physics and technology, the no-cloning theorem resonates with something deeply human. It reminds us that identity itself cannot be perfectly duplicated. Think about memory. Each time we recall an event, the memory shifts slightly, rewritten by the act of remembering. Love, too, resists cloning. You cannot transplant the exact emotional resonance you feel into another person. Even language collapses when trying to express the true coherence of an inner experience. Every attempt to describe a moment is an approximation, a translation, never a duplicate. This mirrors quantum reality itself. A quantum state is a secret told only once. If you miss it, it is gone forever. In a world where digital duplication makes everything feel disposable, the no-cloning theorem restores the idea of rarity, of uniqueness. Each quantum state is like a jazz improvisation, unrepeatable, ephemeral, and singular. You can record it, study it, and simulate it, but the exact performance can never be recreated. It exists only in the moment, just as experiences between people exist only when shared in real time. The theorem is not a frustrating limitation, it is a revelation. It tells us that at the deepest level of reality, identity is not transferable. Each encounter, whether between particles or between people, is precious because it cannot be cloned. This insight challenges us to rethink not only physics but also our philosophy of life. What does it mean to live in a universe where duplication is impossible? Perhaps it means we must treasure each moment as singular. Perhaps it means authenticity, not replication, is the true measure of value. When everything in our society can be faked, forged, or simulated, quantum mechanics whispers a reminder. The most important things, consciousness, love, identity, are uncopyable. They can only be lived once, here and now. And so, the no-cloning theorem is more than just a rule of quantum mechanics. It is a principle that binds physics to philosophy, mathematics to meaning. It shows us that singularity is not a defect but the foundation of reality. The universe is not a library of infinite copies, but a hall of irreplaceable stories, each one written only once. To understand this is to see both physics and life differently. And maybe, just maybe, it teaches us that the rarest things in the universe are also the most important, the things that cannot, and should not, be cloned. Quantum fields, the hidden ocean of reality. Imagine standing at the edge of a vast, unseen ocean, one that ripples even without wind, one that produces brief sparks of form out of its surface, sparks that vanish as quickly as they appear. Modern physics tells us that this strange ocean is not metaphorical, but the most accurate description we currently have of the universe, the reality of quantum fields. For centuries, humanity has thought in terms of things. Ancient philosophers debated the indivisible, atoms, tiny chunks of matter that supposedly formed the bedrock of existence. Centuries later, with the development of modern physics, we upgraded this picture. Particles like electrons, photons, and quarks were hailed as the ultimate Lego blocks of reality. They were imagined as minuscule, hard beads traveling through space. But this image, while useful, is misleading. The deeper we probed with mathematics and experiments, the more it unraveled. Today, physicists understand that particles are not independent building blocks at all. They are temporary excitations, ripples within deeper, continuous fields. An electron is not a speck of matter darting through space, but a localized vibration in the electron field. A photon is not a marble of light, but a wave rising from the electromagnetic field. The vacuum of space is not empty. It's a restless fabric of fields, shimmering with latent energy even at their lowest states. What we call something and nothing are not opposites, but different arrangements of this ever-present sea. This idea forces us to challenge how we think about reality. When you look at a chair, a stone, or even your own body, you're tempted to assign them a solid, fixed identity. But in the language of quantum field theory, these objects are fleeting organizations of vibrations, temporary resonances in an underlying medium. If you pluck a guitar string, the vibration produces a note, but the note is not the string, it's a pattern the string manifests. Similarly, you are not built from fixed particles but from ongoing field patterns harmonizing for a time. And when life ends, those patterns fade, not into nothingness, but back into the silent, eternal field. Death becomes not the erasure of something solid but the cessation of a melody. This shift in worldview is profound. It tells us that individuality is not ultimate. You are a standing wave in a cosmic symphony, a brief arrangement of electron, quark, gluon, and Higgs fields vibrating together. The fields do not vanish when your body ceases. They remain omnipresent. Your existence was never a sealed object but a resonance, and that resonance's silence is part of the larger, ongoing music. From this perspective, connection is not metaphorical. It is physical. The electron field in your body is the same one threading through a distant star. The electromagnetic field that carries starlight into your eyes is continuous with the one filling the void of interstellar space. Every interaction, light striking your retina, atoms bonding in your cells, the push you feel when you touch another hand is a story of fields overlapping and exchanging energy. There are no isolated actors. There is only field meeting field. Even properties we take for granted, like mass, arise from interactions with fields. The Higgs field, for instance, is like an invisible molasses filling the cosmos. Particles moving through it encounter resistance. This is what gives them mass. Without the Higgs field, particles would fly weightless at the speed of light, unable to clump into stars, planets, or life. The very concept of matter having heft is not a built-in feature but the result of interaction. The same holds true for forces. The attraction between electrons and protons is not two little charges tugging at each other, but the electromagnetic field shaping their behavior. When you feel a magnet pulling on a nail, what you're experiencing is not two objects exerting mechanical pressure but the structure of a field shaping matter across space. What's even more staggering is the scope of these fields. They are not localized to one place. They stretch across the entire universe. The electron field is universal. The photon field is universal. When a particle pops into existence, it is not a brand new object arriving from nowhere, it is the field itself revealing a vibration in a specific region. When particles entangle, what links them is not some spooky invisible string, but the fact that their shared field is now in a single, inseparable state. This is why entanglement ignores distance. The underlying field is not bound by our classical sense of locality. The universe is less like a collection of things and more like one continuous medium capable of infinitely complex patterns. Some physicists go even further, suggesting that space and time themselves may not be fundamental but emergent properties of quantum fields. This idea is deeply counterintuitive, but so is nearly everything quantum mechanics has taught us. If correct, it means the universe is not inside space and time. Instead, what we call space arises from the structure of fields, and time is a way of describing how those fields evolve relative to one another. This flips our worldview. Instead of fields existing in space, space may exist because of fields. The fields are the canvas, and space-time is the painting. But here's where things get even more unsettling. If everything we observe, particles, matter, objects, even time itself, is just the surface-level manifestation of deeper fields, what is the true nature of the fields themselves? Are they physical in the way we normally imagine? Are they informational? Are they, as some speculative interpretations suggest, even tied to consciousness? Physics does not answer these questions. It gives us equations, predictions, experimental results. But lurking at the foundation is the possibility that the universe's most basic reality is not material but relational patterns of information encoded in the way fields interact. This resonates uncomfortably with philosophical traditions that have long insisted the world of appearances is not ultimate reality. For human meaning, this perspective is both humbling and liberating. It tells us that permanence is an illusion. You, me, the stars all are temporary dances in an eternal medium. And yet, it also tells us that separation is an illusion. The fields that give rise to your body are the same ones structuring galaxies. When you look at the night sky, the light you see is not a stream of tiny marbles traveling across darkness, but the ripple of a single field, unbroken, carrying information across cosmic distances. When you reach out and touch another person, it is not your particles colliding with theirs, but fields brushing against each other. In this view, individuality, love, decay, and even death are patterns in one shared ocean. Perhaps the most poetic way to think about this is to borrow the metaphor of music. You are not a static object but a note in the symphony of the cosmos. Your birth is the plucking of a string. Your life, the resonance. Your death, the fading of that vibration. The string remains. The possibility of new melodies remains. The field remains. And every star, every thought, every fleeting moment is a ripple in the hidden ocean of quantum fields. To grasp this is to realize you are not merely in the universe. You are the universe, vibrating, briefly, here and now. Does reality collapse? The quantum mystery of existence. Imagine standing on the edge of a mystery so profound that even the brightest scientific minds admit they cannot resolve it. At the heart of quantum mechanics lies a simple but haunting question. Does the wave function, that strange mathematical object representing all possible states of a system, ever truly collapse? Or is collapse just a story we tell ourselves to make sense of an unknowable truth? Picture a darkened theater before a play begins. The stage is quiet, but pregnant with possibility. No actors have entered, no music has started, no lights have revealed the scene. Yet something is there, a silent hum of potential, a vibration of what could be. This is how physicists describe the quantum world. Not a solid photograph of definite outcomes, but a restless haze of overlapping probabilities, like a symphony that could play any song at all. But here's the paradox. Does that symphony exist before an audience hears it? Or is it conjured only when attention falls upon it? This is the essence of the collapse problem. In classical physics, things behave in ways that make intuitive sense. A ball rolls, a planet orbits, a stone sinks. Reality seems to exist whether we notice it or not. But quantum mechanics suggests a far stranger picture. Electrons don't have definite positions until we measure them. Photons can act like both waves and particles, depending on how we look. Schrödinger's cat, trapped in its notorious thought experiment, is both alive and dead until observed. The equations that govern quantum systems, such as Schrödinger's equation, evolve smoothly and deterministically, describing a future full of superpositions. Yet the moment we measure, one outcome snaps into place. A particle here instead of there. A click in a detector. A single note chosen from an orchestra of possibilities. The question is, what caused that choice? Did the wave function really collapse? Or was collapse just an illusion created by our interaction with the system? The Copenhagen interpretation, taught to generations of physicists, sidesteps the question. It simply says, measurement causes collapse. Don't ask how, don't ask why. Just accept that reality crystallizes when observed. But not everyone is satisfied with that. Other interpretations have sprung up, each stranger than the last. The many worlds interpretation proposes that collapse never occurs at all. Every possibility is realized in a branching multiverse. Every quantum choice creates countless new realities, each containing a version of you, asking the same question in slightly different words. Decoherence theory suggests that what looks like collapse is really the system becoming entangled with its environment, spreading its uncertainty until only one outcome is visible to us. Objective collapse models argue that collapse is real and physical, triggered by mass, complexity, or gravity itself. And then there are epistemic interpretations, which claim the wave function represents not reality but knowledge. Collapse isn't a physical event, but a shift in what we know. What makes this puzzle so frustrating is that, so far, all interpretations give the same mathematical predictions. No experiment has distinguished them. Whether you believe in collapsing universes, infinite branching worlds, or probability as mere bookkeeping, the data comes out the same. It may be that we are trapped inside the stage, unable to peek behind the curtain, condemned to wonder whether the show exists without us. This is not a failure of science, but a boundary of human knowledge. We may never know if the wave collapses because collapse and no collapse may be empirically indistinguishable. But here's where the philosophical weight begins to crush down. What does it mean for something to exist if existence cannot be separated from observation? Einstein famously protested, "Does the moon exist only when I look at it?" Quantum mechanics does not give him a comforting answer. In some interpretations, the moon is a probability cloud until measured. In others, it is real but duplicated across countless worlds. In still others, its reality depends not on itself but on interactions and entanglements. The sharp line between observer and observed begins to blur. When you measure a system, you become part of it. The system includes you, and the act of observing is not neutral but transformative, a kind of handshake between subject and object. And yet, for all its philosophical strangeness, quantum mechanics works. It is the foundation of modern technology. Semiconductors, lasers, GPS, quantum computers, MRI scanners. The theory's predictions have been tested to ridiculous precision and never found wanting. Its strangeness is not a bug but a feature. The refusal of the wave function to collapse neatly into certainty may be exactly why it describes the world so accurately. What fascinates me most is how this problem mirrors our own human experience. We crave certainty, closure, definite answers. Did it collapse or didn't it? Is the cat alive or dead? But perhaps reality is telling us something deeper, that the world is not built of static facts but of unfolding possibilities. That what exists is not things, but interactions. Quantum field theory already hints at this. Particles are not little marbles but ripples in invisible fields. An electron is a ripple in the electron field, a photon in the electromagnetic field, the Higgs boson in the Higgs field. Even the vacuum is not empty, but seethes with restless fluctuations, a bubbling sea of potential. Reality, at its core, may be less like a stone and more like a song. Not fixed, but played. Not absolute, but relational. And maybe that's the liberating truth. If collapse is unknowable, then uncertainty is not a defect of reality but its essence. You and I are not spectators outside the experiment, we are part of it. Our choices, our perceptions, our entanglements are woven into the unfolding of the cosmos. When you ask whether the wave function collapses, you're also asking whether you collapse into one version of yourself or spread across infinite possibilities. Do you shape reality, or merely reveal it? Perhaps both. Perhaps neither. Perhaps the real question is why you needed the certainty of collapse in the first place. To me, the beauty of quantum mechanics is not in what it answers, but in what it refuses to resolve. It reminds us that wonder does not require certainty. The moon, whether wave, particle, or probability, is still beautiful. The electron, whether collapsed or uncollapsed, still powers your computer. And you, uncertain, indeterminate, existing somewhere between what you are and what you could be, are part of the same song. Reality may not collapse. It may never have to. Because the ambiguity itself is the music, the trembling chord that has not yet resolved, the curtain that never fully lifts, the superposition that defines what it means to be alive in a universe stranger than we can imagine. And maybe the greatest mistake is thinking we need the song to end to appreciate how beautiful it is while it plays. Spin, the quantum truth beyond rotation. When most people hear the word spin, they think of motion. A spinning top wobbling on a table, a wheel turning on its axle, or the Earth rotating on its invisible pole. But in the quantum world, spin is not motion. It isn't a twirl or a rotation you could ever capture with a slow-motion camera. It is something stronger, a fundamental property of particles, as real as mass or charge, but far less intuitive. Imagine holding a perfectly balanced coin between your fingers, still and silent. Nothing turns, nothing shifts. And yet, someone whispers, "It's spinning." You stare again, baffled, because there is no visible rotation. That's how quantum spin behaves. It exists, but not in the way our instincts want it to. The difficulty is that our language betrays us. The word spin conjures pictures we can't escape. But quantum spin laughs at these metaphors. It isn't a ball twirling, and it isn't motion through space. Instead, it is more like a quantum fingerprint, a number that encodes how a particle interacts, aligns with fields, and obeys the hidden symmetries of nature. Electrons, quarks, neutrinos, and photons all carry spin, not because they are turning, but because their very identity is stamped with this property. Without spin, the architecture of the universe would collapse. Chemistry would fail, stars would not shine, and even the table of elements would not exist. To understand how bizarre this is, imagine trying to describe color to someone who has only ever seen in grayscale. You could talk about wavelengths, you could describe how light interacts with matter, but the essence of redness remains outside the grasp. Spin is like that, something fundamental that refuses to be pictured. Physicists call it quantized angular momentum, meaning it comes only in specific values rather than continuous ranges. An electron has spin -1/2. And this leads to one of the strangest results in all of physics. If you rotate it 360 degrees, it doesn't return to its starting state. You need a full 720-degree turn to come back to the beginning. That statement sounds absurd until you realize it is not metaphor but mathematics. In quantum mechanics, the electron's wave function lives in a space described not by 3 dimensions, but by a deeper symmetry group called SU. This is why electrons behave as if their identity flips when rotated once, only recovering after 2 rotations. To give you a crude analogy, think of a Mobius strip, a surface with one continuous edge. If you trace your finger along it, you return to where you began, but only after looping twice. The analogy is imperfect, but it hints at the alien logic that spin obeys. This property is not just an abstract curiosity. Spin decides whether particles are fermions or bosons. Fermions, like electrons, obey the Pauli exclusion principle, which prevents them from occupying the same quantum state. That single rule explains why atoms have structure, why chemistry exists, and why matter is stable. Bosons, by contrast, can pile into the same state, which is why photons in a laser move in perfect unison, and why certain atoms can collapse into exotic states like Bose-Einstein condensates. The entire divide between matter and force, between what builds the universe and what mediates its interactions, comes from spin. But spin is not just about classification. It governs magnetism, superconductivity, the formation of stars, and the fusion reactions that power the sun. It underpins the standard model of particle physics, where particles of spin 1, like photons and gluons, mediate forces, while spin -1/2 particles build matter itself. Even the Higgs boson has its role, but notice, while the Higgs field gives particles mass, it does not give them spin. Spin is more fundamental, persisting whether a particle is heavy or massless. The photon, with spin 1, has no mass. The electron, with spin -1/2, gains mass through Higgs interaction, but both are forever marked by spin. The remarkable part is how precisely this property has been tested. Physicists have measured the magnetic moment of the electron, a quantity determined by spin, to 11 decimal places. And the results agree with quantum theory exactly. No metaphor can capture this better than the numbers themselves. Spin is real, measurable, and inescapable, even if invisible. And yet, philosophically, spin forces us to rethink what it means to understand something. Our brains evolved to think in pictures: a rotating ball, a turning gear, a planet spinning in the sky. But the quantum world is not a smaller version of ours. It is a realm with its own laws, and spin is a perfect example of that. It reminds us that reality is not obligated to be visualizable. Reality only needs to be consistent. It only needs to work. The deeper truth comes from symmetry. In physics, symmetries dictate conservation laws. Space symmetry gives momentum, time symmetry gives energy, rotational symmetry gives angular momentum. Spin emerges from how particles transform under these symmetries, not as actual rotations but as transformations in abstract mathematical spaces. That's why physicists say spin belongs to representation theory. It defines how particles behave when the universe itself is rotated. This is not metaphorical rotation but algebraic structure, the unseen scaffolding of reality. If you're wondering why this matters beyond theory, look around. Every magnet you hold in your hand, every smartphone, every beam of light in a laser pointer, every burst of energy in the cosmos is governed by spin. The entire digital world, computers, semiconductors, electronics exists because electrons have spin, and because we can manipulate it. In fact, entire fields like spintronics are dedicated to harnessing spin directly for next-generation technology. So what does all this mean beyond physics? Spin is a reminder that not all that is real can be pictured. Not all truths can be drawn. Some things exist only as equations, principles, or patterns. The quantum world forces us to accept that intuition is not the measure of reality. And maybe, in a strange way, that lesson applies to us too. You have qualities no one can see, traits that do not live in your actions but in your potential, in the symmetries of your mind. Like particles, you might look still, but carry unseen momentum. You may appear simple, but hold depths that only emerge under the right conditions. The universe, it seems, is not a painting we can stare at until we understand it. It is more like a language, written in mathematics, structured by rules, and expressed through invisible patterns. Spin is one of those rules, a quiet, stubborn truth that keeps matter together, drives the stars, and shapes the invisible scaffolding of everything. So if you ever feel confused that reality cannot be reduced to pictures, take heart. Every physicist who has wrestled with spin has felt the same disorientation. Because spin is the point where metaphor dies and only mathematics remains. It is not rotation, not motion, not something you can imagine, but it is real. It is as real as the ground you stand on, as the breath you take, as the light that reaches your eyes. Spin is not the story of rotation. It is the story of identity. It is the universe's way of saying, not everything that exists must be visible, and not everything that is true must be intuitive. Sometimes, the deepest truths are those we cannot picture at all. The quantum measurement problem. When reality waits to be seen. Imagine standing in front of a mirror that refuses to show you as you are. Instead, it reflects endless versions of you, one smiling, another frowning, one walking away, another reaching forward. None of these reflections are fixed until you choose to look more closely. This unsettling metaphor captures the essence of one of the deepest mysteries in modern science, the quantum measurement problem. At its heart lies a question so deceptively simple that it shakes the very foundation of what we mean by real. In classical physics, the world is straightforward. A ball is either on the table or it isn't. A star shines whether or not you look at it. Measurement merely reveals what already exists. But in the quantum world, things don't behave this way. Before we measure them, particles exist in superpositions, a mathematical blur of all possible states. The electron isn't here or there. It's both. A photon doesn't pick a path through a slit. It explores every path simultaneously. These possibilities are described elegantly by Schrödinger's wave equation, which evolves smoothly and predictably. And yet, when we measure, this calm river of probabilities crashes into a single result. The wave function collapses, one possibility crystallizes into reality, and all the other potential outcomes vanish without a trace. This collapse isn't described by the equations of quantum mechanics. It's sudden, irreversible, and strangely outside the rules of the theory itself. It's as if the universe is a script being written as it's performed, yet no one agrees who the author is or if the script even existed before the curtain rose. The theory works flawlessly at predicting probabilities, but it is silent on what measurement actually is. That silence has been a source of debate for nearly a century. Different interpretations attempt to fill the gap. The Copenhagen interpretation, historically dominant, suggests that physical reality doesn't exist until observed. In this view, looking is not passive. It conjures the world into being. But this raises troubling questions. What exactly counts as an observer? Is it a conscious mind, a detector, or simply any physical interaction? Why should human awareness, something that emerged late in the universe's history, hold the power to shape reality? The many worlds interpretation sidesteps collapse entirely. It argues that all possible outcomes occur, but in separate branches of the universe. You don't collapse Schrödinger's cat into alive or dead, you split into two versions of yourself, each witnessing a different outcome. It's elegant in its consistency, but it comes with a price: infinite, ever-branching realities. If every quantum event creates a new universe, we must accept an unfathomable number of parallel worlds. It's a breathtaking vision, but also deeply unsettling. Other theories propose spontaneous collapse. The Ghirardi-Rimini-Weber model, for example, imagines that wave functions collapse randomly on their own, governed by new probabilistic laws. This avoids the mystery of observers, but introduces new constants and mechanisms that have never been observed experimentally. Decoherence offers another perspective. It explains how superpositions appear to vanish when quantum systems interact with their environments. The interference between possibilities spreads out and becomes inaccessible, making the system appear classical. Yet decoherence alone doesn't solve the riddle, it only explains why we don't see quantum weirdness in everyday life, not why one outcome becomes real. Some philosophers and physicists reframe the problem entirely. In cubism, or quantum Bayesianism, the wave function doesn't describe objective reality at all. Instead, it represents an individual's personal knowledge or beliefs about a system. Collapse isn't a physical process. It's a mental update, like revising your expectations after flipping a coin and seeing heads. But this leads to new puzzles. If quantum states are subjective, how do multiple observers ever agree on outcomes? What guarantees consistency in a shared world? What makes the measurement problem so profound is that it forces us to confront the boundary between physics and philosophy. Are we uncovering truths about the universe, or are we discovering the limits of human perspective? Perhaps the very distinction between observer and observed is an illusion. In quantum mechanics, observation is participation. You cannot measure without disturbing, cannot look without leaving fingerprints. The act of asking the question changes the answer. Think of it this way. In classical science, the universe is a stage and we are the audience. The play unfolds whether or not we watch. But in quantum physics, we are not in the audience, we are part of the cast. Our interactions help determine the script. This is not a bug in the theory. It's woven into its fabric. Every time we observe, we influence. Every time we measure, we participate. That idea unsettles us because it blurs the neat categories we've grown comfortable with. Are we separate from reality, standing outside and observing? Or are we embedded within it, threads in the cosmic tapestry? The quantum world hints at the latter. Measurement may not be a special, isolated event, it may be the universe unfolding naturally, with us entangled inside it. If so, then your every thought, your every act of curiosity, is part of the cosmic equation. You are not outside reality, you are woven into its very structure. This is why the measurement problem refuses to die. It is not merely a technical glitch in physics. It is a mirror held up to our understanding of existence. Each interpretation, Copenhagen, many worlds, spontaneous collapse, decoherence, cubism, offers a fragment of the truth, but none resolves the whole. The deeper we peer, the more we realize that our categories of real, observer, and measurement may themselves be flawed. Perhaps the question is not when the wave function collapses, but whether collapse is even the right concept. Perhaps what we call collapse is simply our limited view of a much larger process, like mistaking a shadow for the object that casts it. And maybe the ultimate lesson is that physics doesn't banish mystery, it frames it. The goal is not always to find answers, but to refine the questions. So when we ask, what is real? The universe replies with another question. What do you mean by real? The mirrors don't show us fixed truths, they show possibilities. And each possibility exists until our gaze crystallizes one into being. The measurement problem reminds us that knowing is inseparable from being, that certainty is not a property of the universe but an experience in the mind. Nearly a century after quantum mechanics broke the glass of classical certainty, we are still staring into the fog. The math works. The predictions match experiments. The technology based on it, from lasers to computers, functions flawlessly. And yet, the meaning remains elusive. That tension is not a failure of physics. It is part of its beauty. Reality may not be something that waits for us to discover it like a fossil in stone. It may be something that coalesces in the act of discovery itself. And maybe that is the gift of the measurement problem. Not a final answer, but an invitation to wonder. To accept that reality is deeper, stranger, and more participatory than our metaphors allow. To recognize that when we measure, we are not simply reading the universe, we are entangled with it, co-creating its story. Perhaps physics is not about removing mystery but about teaching us how to live with it more profoundly. Because in the end, what matters is not whether the wave function collapses or branches or decoheres. What matters is that when we look, something appears. And in that moment, reality becomes real for us. That act of looking, of asking, of daring to wonder, that may be the truest measurement of all. Electrons are clouds, not orbits, the hidden truth of quantum reality. Electrons are not obedient planets circling a sun-like nucleus. That image, taught to us in school, was a comforting metaphor, a stepping stone that made the invisible seem familiar. But it is not reality. The true behavior of electrons is stranger, more abstract, and more unsettling than any neat diagram of miniature solar systems. Electrons do not orbit. They exist as clouds of probability, statistical whispers that suggest where they might be, but never exactly where they are. To understand this, we need to dismantle the old picture and step into the quantum world where certainty dissolves into possibility. The planetary model was never meant to be final truth. It was a placeholder, a story that echoed cosmic order so that we could imagine the atom. But when physicists began probing deeper through spectroscopy, quantum equations, and direct experiments, the illusion cracked. Instead of neat circular tracks, they found diffuse distributions, regions of likelihood. And the mathematics that governs them is not Newtonian mechanics, but Schrödinger's wave equation. This equation doesn't chart a path. It defines a wave function, a spread of probabilities. It tells us not where the electron is, but how likely it is to be in different places. Imagine mist rather than marbles, fog instead of balls in orbit. The electron is not hiding inside that fog, waiting for us to catch it. The fog is the electron. And this realization reshaped physics. Why does this matter? Because these clouds are not decorative metaphors. They are experimentally confirmed. Scanning tunneling microscopes, atomic spectroscopy, and quantum interference all reveal the same thing. Electrons leave fingerprints of probability, not trajectories. Their presence emerges in patterns, not paths. And those patterns, strange lobes, clovers, dumbbells, aren't fantasy. They are dictated by quantum numbers, symmetries, and the Pauli exclusion principle. Each electron in an atom must occupy a unique quantum state, and that rule alone explains why matter has volume. If electrons could all pile into the same place, matter would collapse. Your chair, your body, the planet itself would crumble. Instead, exclusion forces electrons to spread into distinct states, filling different clouds and giving atoms depth. The solidity of the world is not built on little hard balls, but on forbidden sameness. It's quantum refusal that keeps your body from sinking through the seat you're in. Think about how revolutionary this is. In classical logic, when you ask, where is the electron? The answer should be a definite location, like a coin under a cup, hidden but real. Quantum mechanics rejects that logic. Before measurement, the electron doesn't have a location. It has a distribution. It's not simply unknown, it is undefined. And when you do measure it, the wave function collapses into one outcome, but only temporarily. The moment you stop looking, it resumes its ghostly spread. The universe at this scale does not speak in absolutes. It speaks in amplitudes, in patterns of maybe. And this is not philosophical hand-waving. This is physics. It explains chemistry, bonding, light emission, even the periodic table. Covalent bonds, for example, aren't little sticks between dots, they're overlapping probability clouds, electrons shared not as objects but as smeared out presences. Electricity is not marbles flowing down a wire, it's the migration of disturbances in the electron field. Light itself, photons, is released when electrons shift between energy states, collapsing from one cloud distribution into another. At the deepest level, quantum field theory reframes everything further. Electrons aren't really particles at all, but excitations in a universal electron field. A localized ripple in that field looks like an electron. The wave function describes the allowed resonances of this ripple when trapped by an atomic nucleus. Stationary states emerge, like standing waves on a violin string. These stationary states are what we call orbitals, though they are not orbits. They're patterns of vibration, symmetries of possibility. And those patterns don't arise in isolation. They're shaped by the electromagnetic field, by nuclear charge, by other electrons whose exclusion reshapes the available states. Atoms are not miniature solar systems. They are quantum symphonies, collective dances of fields tuned by invisible rules. Even the vacuum is not silent. What we call empty space seethes with fluctuations, virtual particles popping in and out of existence, Higgs field excitations giving mass to matter, jittering foam at scales we can barely imagine. The electron exists within this restless vacuum, not against it. Its probability cloud is not a static shell. It is a standing wave in a vibrating field, sculpted by equations but animated by uncertainty. And these clouds take surreal shapes. Spheres, dumbbells, four-leaf clovers, rings. Not because electrons carve those patterns, but because the mathematics of wave functions allows them. Scientists have mapped these shapes experimentally, not by seeing an electron directly, but by collecting the imprints of countless interactions. When you look at those strange diagrams, you're looking at the fingerprints of possibility itself. This view transforms how we see reality. You are not made of tiny solid marbles, but of smeared clouds of probability stabilized by exclusion, arranged by symmetry, and expressed through quantum rules. The classical metaphor dissolves, replaced by something both more abstract and more poetic. And there is a human lesson hiding in it. Just as electrons don't orbit, neither do you. You don't circle your life in neat paths. You hover, shift, resonate. Your presence is not a fixed location but a pattern emerging from possibilities. Your identity, too, is a cloud, a superposition of past experiences, future hopes, and the collapse of choices made in the present moment. You are not a marble. You are a mist, and perhaps that is the deeper truth quantum mechanics whispers to us. The universe is not built from hard stuff, but from relationships, symmetries, and probabilities. The structures we touch are stabilized by rules of exclusion and resonance, not by tiny planets circling centers. The very firmness of the chair beneath you, the bonds in your body, the light in your eyes all depend on clouds of possibility. What you perceive as reality is a collapse of options into temporary certainty. Beyond what you see, an ocean of potential remains. Electrons are not orbits, but clouds. And so are you. What you call solid existence is a statistical agreement, a fragile pattern etched from uncertainty. And that, paradoxically, is the most solid truth we have. The secret weight of nothing, how the quantum vacuum shapes reality. We tend to think of nothingness as absence, a blank slate, a canvas devoid of matter or energy. But modern physics suggests something far stranger. What we call empty space is not empty at all. It has weight, density, pressure. It influences stars, galaxies, and the very structure of space-time. In truth, the vacuum is less a void and more like an invisible stagehand, moving the props and pulling the strings of the cosmic play without ever appearing in the spotlight. If you picture yourself inside a vast abandoned cathedral, where silence seems absolute, you might think you are standing in emptiness. Yet, even in that silence, there is vibration, resonance, an invisible hum beneath perception. The quantum vacuum is like that hum, a hidden orchestra at the foundation of reality. In classical physics, a vacuum meant a true absence of particles, a space stripped clean, like an erased chalkboard. But quantum field theory completely overturned this definition. Instead of a barren stage, the vacuum is understood as the lowest energy configuration of fields that permeate the universe. And crucially, that lowest energy is not zero. Even at its quietest, space seethes with fluctuations, what physicists call zero-point energy. These fluctuations are unavoidable because of the uncertainty principle, which forbids absolute stillness at the quantum level. Imagine a violin string tightened but untouched. Even if you never bow across it, it still quivers faintly. The vacuum is that faint vibration, magnified across all of space-time. These fluctuations are not theoretical curiosities but measurable phenomena. The Casimir effect demonstrates this beautifully. Two metal plates placed extremely close together in a vacuum experience a subtle force pushing them together, not because of any hidden particles, but because the vacuum itself has fewer modes of electromagnetic fluctuation between the plates than outside. The imbalance produces pressure, proving that nothing can act like a force. Another example, the Lamb shift, shows how vacuum fluctuations alter the energy levels of electrons in atoms. These subtle effects shape the behavior of matter at the most fundamental level, making the vacuum not a passive backdrop but an active participant in physics. But perhaps the most profound role of the vacuum is cosmic. Its energy density contributes to the cosmological constant, what we observe as dark energy. This is the strange, repulsive pressure that accelerates the expansion of the universe. Unlike gravity, which pulls, vacuum pressure pushes, stretching space-time itself. This is not poetic exaggeration. Astronomers measure it in the redshift of distant supernovae, in the distribution of galaxies, and in the ripples of the cosmic microwave background. The fate of the entire universe, whether it expands forever, collapses, or rips apart, hinges on the properties of the vacuum. The Higgs field is perhaps the most famous example of a vacuum field shaping reality. It pervades the cosmos with a non-zero value, and particles like electrons and quarks gain mass only through their interactions with it. Without the Higgs field, the universe would be a collection of massless particles zipping around at light speed, incapable of forming atoms, molecules, or life. In other words, the vacuum is not just background scenery, it is the sculptor that carves structure from chaos. Now here is where things become even more unsettling. The vacuum hasn't always been what it is now. In the early universe, as it cooled, the vacuum underwent phase transitions, like water freezing into ice. Each transition changed the values of fields and forces, altering what particles could exist and how they interacted. The Higgs field itself settled into its current state during one of these transitions. What we call the constants of nature, the masses of particles, the strength of forces, are really just the frozen consequences of vacuum history. If the vacuum had cooled differently, the universe itself would have been unrecognizable, maybe incapable of chemistry, stars, or life. What we call laws of physics are, in a sense, the properties of our current vacuum. This raises philosophical questions as much as scientific ones. If the vacuum is the foundation of reality, does that mean the distinction between something and nothing is illusory? When we say, space is empty, what we really mean is that no particles are present, but the fields remain, humming with activity. Nothingness, in this view, is never truly nothing, it is always something waiting to act. This makes us reconsider concepts like existence, absence, and creation. When cosmologists propose that the universe may have emerged from a fluctuation of the vacuum, they are not saying it came from nothing in the classical sense, but from a field that never fully rests. Think about that for a moment. Every star you see at night, every atom in your body, every beat of your heart depends on the vacuum's hidden structure. We are suspended in a sea of fields, sculpted by the quiet energy of nothing. And yet, we rarely think of it. We treat emptiness as irrelevant when, in truth, it is the most fundamental presence there is. Even silence is a song. This realization forces us to rethink our place in the universe. If the vacuum itself can change, if different vacuum exist, then perhaps other universes, with different physical laws, are possible. The multiverse hypothesis is, in part, a consequence of this line of thought. Our universe may be one bubble of vacuum in a much larger reality, each bubble with its own properties. The fact that our vacuum permits life may not be evidence of design, but simply one configuration among countless possibilities. What is most profound is how little we still know. Quantum field theory can describe the vacuum's fluctuations, but when physicists calculate the vacuum's energy density, the result is wildly off, many orders of magnitude greater than what we observe as dark energy. This mismatch, called the cosmological constant problem, is one of the greatest unsolved puzzles in physics. How can the vacuum have so much theoretical energy yet produce only a tiny observable effect? Perhaps the true structure of the vacuum is far deeper than we imagine. Some propose that it hides new symmetries, dimensions, or mechanisms we have not yet discovered. So the next time you look into the night sky and think of space as empty, remember this: between every galaxy, between every atom, between your hands as you clasp them together, the vacuum vibrates. It presses outward on the universe, gives mass to matter, alters atomic structure, and may decide the ultimate fate of everything. The quantum vacuum is not nothing, it is everything disguised as nothing. A silence that is always singing, a void that creates worlds, a presence so omnipresent that we mistake it for absence. To understand the vacuum is to glimpse the hidden architecture of reality, the true weight of nothing. Reality Unwritten: How Quantum Physics Reveals a Universe of Possibilities. Imagine walking into a library where every book sits on the shelf without a title. Their spines are blank, their covers mute, their pages empty. Only when you reach out to touch one does it reveal its story. A moment earlier, that book contained every tale ever written, every character alive and dead, every ending both joyous and tragic. The act of choosing forces a narrative to crystallize from uncertainty into existence. This imagery is not a fantasy novel setup, it is a metaphor for the quantum world, the invisible foundation of reality itself. In quantum mechanics, particles do not arrive with properties waiting to be discovered. They exist in a haze of potential, in a superposition of all allowable states, until we demand an answer through measurement. An electron isn't spinning up or down until you check. A photon isn't following one path or another, it explores every possibility simultaneously until observation locks it into a choice. This might sound poetic, but it is grounded in mathematics and experiment. Quantum physics insists that reality, at its most fundamental level, is not built of fixed certainties but of probabilities waiting to be realized. The famous double-slit experiment makes this idea concrete. Fire a single electron or photon at two slits, and instead of choosing a single path, it behaves like a wave, interfering with itself as though it traveled both routes at once. Yet the moment you try to catch it in the act, by measuring which slit it passed through, the wave collapses. The interference vanishes, replaced by the pattern of particles choosing one slit or the other. The simple act of asking the question creates the answer. This raises one of the strangest and deepest mysteries of modern science. Reality does not exist independently of our interaction with it. The observer is not a passive witness, but an active participant in the formation of the world. This insight dismantles the comforting assumptions of classical physics. In Newton's universe, objects simply are. A planet has a location whether or not you look. A rock has mass regardless of whether you weigh it. Properties are stable, objective facts. But quantum mechanics turns that certainty into mist. Position, spin, momentum, these are not fixed values hiding in the shadows, waiting for our instruments to reveal them. They are undefined until observed. Even more shocking, the Kochen-Specker theorem demonstrates that there is no consistent set of hidden instructions that could predetermine all possible answers. Reality is contextual. What you find depends on what you ask. An electron measured along one axis will give one result, but shift the context of the question, and reality reshapes itself. This participatory nature of reality doesn't mean the universe is chaotic nonsense. On the contrary, quantum theory has proven to be the most accurate predictive framework we've ever built. Its mathematics allows us to engineer semiconductors, lasers, superconductors, quantum computers, and medical imaging devices. It powers the everyday technologies of the digital world while also enabling exotic phenomena like quantum teleportation and entanglement. Nature, in its experiments, agrees with the strange mathematics. The uncertainty isn't a failure of knowledge. It is a fundamental truth. Reality is not a static archive but a living conversation between possibility and observation. Think about what that implies. If every particle in your body exists in a sea of probabilities until measured, then solidity itself is an illusion of stability. Your hand feels firm because the probabilities have stacked into a remarkably consistent structure. But dive deeper into the atoms, into the subatomic domain, uncertainty dissolves into waves of maybe. Every atom is a story that could have been written in countless ways, but the version you inhabit is just one among many potential scripts. Here's where the philosophical weight becomes clear. You are not outside this process. As an observer, your choices of what to measure, how to measure, and when to measure are part of the fabric of what becomes real. You don't merely watch the universe unfold. You help decide how it unfolds. Every observation is a vote in the cosmic ballot box, collapsing one set of possibilities and discarding countless others. Some interpretations of quantum mechanics, the many worlds, for instance, suggest those other possibilities don't die but continue in parallel realities. Others, like the Copenhagen interpretation, argue they simply vanish, never realized. Still others suggest nature itself randomly selects one outcome when forced. Regardless of the interpretation, they all agree. The particle had no fixed properties before you looked. This concept can ripple outward from physics into philosophy, psychology, and even identity. Perhaps you, too, are not a fixed being but a superposition of roles and potentials. Teacher and student, friend and stranger, confident and uncertain all exist as possibilities until called forth in context. You are shaped by the interactions you have, just as an electron is shaped by the axis along which it is measured. Identity may not be a static truth but a relational process, emerging in the moment, collapsing from potential into presence. Quantum mechanics suggests that the universe is not woven from hard threads of being but from waves of uncertainty. This uncertainty is not weakness, it is the source of structure, creativity, and complexity. Without probabilities to guide chemistry, there would be no molecules, no life, no consciousness. The same uncertainty that unsettles philosophers also enables your very existence. Beneath every fact lies a whisper of alternatives, unseen but vital, like shadows of unrealized worlds. So what lesson should we take from this? First, that reality is not a fixed, objective stage upon which we act. It is a participatory story, co-authored by the universe and the observers within it. Second, that what we perceive as solid certainty is underpinned by an ocean of possibility, a reminder of the fragility and wonder of existence. And third, that by recognizing the participatory nature of reality, we may also better understand ourselves not as rigid, predetermined beings, but as flexible, contextual participants in a cosmic unfolding. Quantum mechanics doesn't just describe particles. It describes a worldview where observation and interaction are inseparable from reality itself. It suggests that the universe is not a static book we open to read, but a story still being written, page by page, question by question. Every measurement, every observation, every conscious interaction is like a hand reaching out to touch a book in that library of unwritten stories. And in that instant, the words appear. Reality crystallizes. The story continues. The final message may be unsettling, but it is profoundly human. You are not a spectator in this universe. You are a participant, a collaborator, an author. The particles wait, undefined, until your presence, your question, your observation calls them into being. And in that sense, existence itself is not a destination we arrive at, it is an unfolding dialogue between what could be and what is. The universe, then, is not a collection of things but a collection of questions. And you are among those questions, helping shape the answers with every choice you make.